mic is now suddenly very loud, and now it's quiet, and now it's probably a reasonable volume. So you can tell that we did a lot of setup and prep work for this. Regardless, thank you for attending. I think this is going to be a wonderful session, and I'm going to get the show on the road. No reason to dilly-dally here. So what we're going to do is in 10 minutes try to make you not an expert, but have a reasonable understanding of host networking in general. Then we have 3 papers which have things in common and that maybe require some special information. So that's what we're going to do. We're going to cover general problems, and then we're going to get into some paper-specific background. Okay, so the first question that we would like to answer is, what is host networking? We're at NSDI. Hopefully we know what networking is. However, host networking is this sort of special, interesting flavor. Particular, at NSDI, we spend most of our time talking about this crossbar or logical crossbar here in the middle connecting our CPUs. With host networking, what we're really caring about is sort of the CPUs and cores themselves and how we're able to generate and send and process networks to and from the network. Okay, so the important thing here is that host networking enables application on one server to communicate with another. So unlike most things in NSDI, where we're going to look at things, like I said, in the core, we're now looking at the edge. Okay, so what does this edge look like? It turns out that we can separate into roughly 3 significant portions here. First, we have our applications and containers running in user space. They're connecting possibly through an operating system network stack. Then finally, they connect out to the NIC. But so the big part here is that we have applications, and we have a NIC, which is some special hardware that we can talk to, and it will send and receive network cards. One thing I'd like to point out is that I show application 1 going through the network stack, whereas application 2 bypasses it. This is going to be about kernel bypass networking. It turns out the operating system isn't required in this picture. We'll get more into this in some details later. Okay, so finally, to give a little bit of general information, how are we going to be measuring and understanding performance in our systems? So one of the big things here is that unlike in core networking, we have this sort of 3rd or 4th dimension that we normally don't care about. So the big one here is CPU utilization. And a big trend in host networking is that if you have to burn too many cores to drive line rate or do your networking, it's not going to be worth it, because you would be better off using those cores just for something else for your application. Another thing here is that we have this throughput sensitive thing. That's when your CPU core or maybe your NIC execution units are running at full line rate, or I'm sorry, full throughput, but not driving line rate. Then finally, a big thing that we're going to see as part of this talk is also that high-level application performance metrics matter. We're going to care a lot here about things like operations per second, as much as possible from an application standpoint. Then things are big data, or other sort of OLDI jobs. We're going to look at tail latency, job completion times, these sorts of things. Okay, so hopefully I'm not taking too long, but we're now here to general problems. And the big general problem that we have to deal with in host networking is that line rates are increasing while our core performance has relatively steadied off and flatline. So this is sort of the big overarching problem that in some aspect all 3 of our papers in this session are going to be talking about. So the figure on the left is traffic in Google's data center network. The figure here on the right is standardized Ethernet speeds. It's important to know that 200 and 400 gigabit Ethernet have already been standardized and are becoming available in Ethernet NICs today. Okay, so one of the reasons that driving these increasing line rates is a problem is because we're getting closer and closer that our per packet processing time that we have to meet is now very close to our memory access latency. So here we can see that even if we're processing in maximum sized packets at line rate at 100 gigabit per second, we have 120 nanoseconds per packet to do so, when that's roughly about the exact same amount of time we have for a single memory access. Okay, then finally, one of the big things that we have here is that we don't necessarily care Well, we care in particular about the performance of all of these different applications, but we also care about the performance as an ensemble. That's this idea that we want to be able to pack and co-locate as many applications onto a server as possible to increase our overall utilization and efficiency, but doing so typically yields to performance problems. What I mean with this is that we typically have these applications with differing performance goals. On one hand, we have Memcached, very latency sensitive, a Spark, very bandwidth sensitive, and these tend to compete with each other. But once again, I've drawn in this sort of third type of flow, which is this high throughput, which, as you can imagine, it's something doing these sort of small RPCs, but it's doing them as fast as possible. These aren't really a clearly defined category, but it's important to know that all of these different applications have performance isolation problems when they're co-located. Okay, I'm probably taking too long, but so I can hopefully get to this very quickly. These are three important tidbits of information I think necessary to understand tomorrow's papers. So the first one is programmable scheduling. Okay, and for this, we have the push-in, first-out queue as our fundamental primitive for programmable scheduling in networks today. So what we have here is a priority queue where to compute our scheduling, we're going to compute some sort of rank into this queue, then we're going to dequeue from the front. So you can see here that we'll have our flow come in, we'll compute a rank, we'll use that rank to enqueue in a queue. The important thing here is that it recently, Mittal et al. Showed that you can use this in a single hop within a single node, scheduling a single resource to implement any scheduling algorithm. So what we have here is a fundamental programmable scheduling primitive. And this is important. We not only can now do programmable scheduling across a single queue, but we can now do programmable scheduling across some sort of complex hierarchical scheduling function. So in this case, we're going to use our programmable queues, our PIFOS, to build hierarchical packet scheduling. So I'll hide a little bit of the details here, but you can see the paper for more information. Okay, so this brings us to kernel bypass. I alluded to this earlier, and so what we see was what we're doing is we're going from the figure on the left, where we have the kernel sort of allocating our threads and cores and allocating access to NIC resources. And instead what we do is we do a direct assignment of NIC resources to our application. This allows us to get significantly better performance, allows us to get lower latency, allows us to do a lot of things to save CPU. So this is a big and important trend. Importantly, we now have applications that can completely and totally in parallel, without communicating with each other, send packets to the NIC. RDMA is really just a collection of special NIC offloads that allow you to do things like access NIC memory while bypassing the CPU. This is illustrated in the figure here. When you're considering RDMA, the big things to know about is that we really have three entities at every single server. We have RAM, CPU, and the NIC. And depending on how you want to access memory, you can involve some combination of those as you'd like. Okay, but so a big limitation here is that we've now offloaded things to the NIC as a coprocessor, and it's now responsible for scheduling and deciding between packets. So to get into that in a little bit more detail, we're going to have our first paper look and compare against DPDK or NetMap style kernel bypass and RDMA style kernel bypass. And the big difference here is in these two, the management is done in software and DPDK style NetMap, whereas management is done in the RDNIC hardware itself and RDMA style kernel bypass. While DPDK allows us to now have predictable performance and constant NIC state, the trade-off we're paying is that we have significantly higher CPU utilization to do so. Okay, so another big point that I'll bring up for my talk that's coming up, please everyone attend, is that now packet scheduling when we're using things like kernel bypass, or really even just the NIC for parallelism, is controlled entirely by the NIC. That's because we have different queues, all the applications are using the queues in parallel. It's now up to my NIC how to decide how to schedule packets. Unfortunately, it doesn't schedule them well. I'm going to tell you tomorrow about how we're going to schedule things better. Okay, we're wrapping things up. We're a little bit behind time. But so we also have this big problem of CPU utilization of networking is too high, especially when we're doing things that we did at 1 gig now at 100 gig. These are 3 sort of general trends and techniques that you're going to see and have talked about for reducing CPU utilization. The first is that instead of processing small packets, we process large segments. The Linux kernel does this aggressively with transmit segmentation offload. They use 64K segments. If we can't use large segments, we'll use batching, where we process many small packets at once. This improves things like cache utilization, and it overall improves performance. And finally, we'll add in parallelism. This idea we have different cores operating in parallel on different NIC resources. They never talk to each other. We sort of get the ideal linear scaling, or close to it. Okay. Then finally, we have some PCIe limitations. This is the idea that our NIC isn't even the last network. We now have a network inside our CPU in addition to our cache coherency networks. Like I said, we're low on time. In general, this has its own throughput and latency limitations. You don't want to exceed them. Okay. So in conclusion, I've taken too much time to tell you about host networking. I think it's important, yet very often neglected area of research, so I'm excited that we get to hear about it in our first session of NSDI. And I think, hopefully, you've taken away that there are many sort of significant and fundamental problems still left in networking. Okay, well, like I said, I'm over time, so thank you for having me. I really appreciate the audience. If you have any questions, come find me after the session.
You can actually ask questions right now.
Oh, that'd be great.
Okay, I'm back for the second of many times that you'll see me tonight. And this time, I'm actually going to try and preview the distributed systems session, which is the second session tomorrow. Now, distributed systems is a rather large topic. I teach a semester-long class on it, and I feel like I can never cover everything. So I can definitely not cover everything in 10 minutes. Instead, NSDI distributed system session is mostly about key value stores and cryptocurrency. I'm not even going to cover cryptocurrencies. Those are hard and annoying, so I'm just going to look at the key value store bit. I'll tell you how cryptocurrency fits in, though. So let's start with what are key value stores. So everyone here know what hash maps are? Any concerns about hash maps? OK, so a key value store is just a hash map that someone can access over the network. Now, hash maps are beautiful things because you can fit anything into them. You can refer to them with keys. You can make keys however you want. They're really a nice universal abstraction. And usually, we talk about key value stores, which have 4 classes of operations: create, delete, update, and read. So here are my ways of saying this, which is you can do get, set, and delete. And in general, when clients issue these commands, you'll get them. You'll get responses in some order. And what happens with ordering gives you the consistency semantics of the key value store. Oh, and finally, these key value stores are super popular. I don't people care about impact. These things are used all over the place. You have Amazon giving you Dynamo. You have Cassandra. You have Redis. A lot of these things. So one issue with these key value stores is scalability. So regardless of what consistency semantics you use, if you have a computer, or let's say you have a core can serve only so many requests in parallel before these requests start queuing up. You have n cores, you still have queues. So the problem then becomes that because of these queues, the latency that you experience in the system is now proportional to the number of requests you're seeing. And so if, I don't know, you happen to own a website which ends with book, you might have several different people accessing your website, and they're suddenly stuck behind each other. So you want to somehow scale these. So one proposed solution to scaling these is, hey, let's, instead of running one key value store, run n key value stores. Now, running n has two benefits. So the first one is, so remember I said you could have consistency semantics. If you had consistency semantics and you just replicated the key value store, so you had many copies, you would induce some amount of load between them because they'd need to agree with each other. By not sharing anything, by having this sort of share nothing parallelism, you can scale arbitrarily by just adding more shards. And so now, instead of people queuing up, as happened in my previous example, all three of these clients can get responses at the same time. So you can see that sharding helps with scalability. So this is really powerful. You can increase the number of shards to scale. It's how web scale services have been doing it forever. But there is a huge problem with sharding, which is we need to decide how do you partition items or keys across these shards. Now, the reason this is a problem is because of this stupid curve, which always annoys me. It's a power law distribution, which means that some percentage of the items are very popular and some percentage is not. So, for example, for those of you who are on Twitter, Twitter accounts belonging to people like Lady Gaga have millions of followers. Twitter accounts belonging to people like me have hundreds of followers. The same website serves both. So now, if you look at the shard that contains Lady Gaga, it's getting a lot more hits than my shard. And that shard is the one that's hard to scale, right? So, as I said, content popularity is one of these things. Now, the thing is, for many things on the web, actually content size is also one of these things. If you look at all of the web pages and web objects that you're loading, you'll find that sizes vary by several orders of magnitude. Some files are several bytes long, some files are several megabytes long, some people have ISOs on their website which are 4 gigabytes, might hurt you. So why is this a problem? Because the fact that you have popularity and sizing means that there's a difference in the number of clients that is arriving at each shard, so the queue length at each shard, and also the amount of time it takes to carry out any operation. So even if you have the same number of people waiting in a queue, if some operations take 10 times longer, you're going to be really sad. OK. The other problem that shows up is cross-shard consistency. So remember how I said shards are completely independent? That's making an assumption that your workload allows partitioning in this way. So again, consider Twitter or Facebook or one of these usual websites, right? So Facebook in particular allows bidirectional relationships. So friends, your friends are if you are someone's friend, they are also your friend. So at any moment in time when you decide to establish that relationship, Facebook needs to change both your data and their data. If you want to get consistency across these two, you need to somehow deal with the fact that these things are not entirely independent anymore. You somehow are coordinating between them. And so the usual answer to this sort of coordination issue is first, just avoid it or relax this requirement. So if you're Facebook, it really doesn't matter if the fact that you are someone's friend and they are your friend appear at slightly different times, as long as they appear eventually, people are happy, no one cares, whatever. But the other big hammer is you can use protocols like 2PC and 3PC, and you can go read about these. It would roughly take me 55 minutes to explain why they work and how they work, which is more time than I have available. OK. So at NSDI this year, we have 2 papers on sharding that look at 2 different aspects of sharding. So the first one is a paper called Minos, which comes out of EPFL by Didona and Willy Zwanapel. And the idea here is that, hey, look, people have been considering size-aware sharding for a while, popularity-aware sharding for a while, but people haven't been considering size-aware sharding. And what they show is that there's a difference in the amount of time it's taking to process large objects versus small objects. So their approach to this is to go figure out how many large objects, or what constitutes a large object, put them on a different shard, and figure out what are small objects, and put them on many different other shards. The second paper is Monoxide, which is by Wang and Wang. This is not a key value store paper. This is a cryptocurrency paper. But what is cool about it is it's talking about sharding cryptocurrency, because cryptocurrencies currently have a scalability limit exactly for the same reason. You're committing lots of data. You have some consistency requirements. As you're doing this, and more people start committing these things slow down. So how can you basically go and shard them? And they have some interesting ways for how to get cross-shard consistency and how to avoid attacks which are common in these cryptocurrency things. OK, so another solution to this scaling dilemma, which is often used with sharding, is to cache. So remember my thing with Lady Gaga? Well, no matter how well you shard, whatever shard Lady Gaga ends up on is going to have lots and lots of clients. So we really need to scale that shard up too. And so the idea here is that you could put a cache in front of it. And this works really well when you have read-heavy workloads, which are workloads where you have very infrequent changes. So because changes are infrequent, you can have several caches, not have a lot of traffic invalidating the caches, and still get lots of scalability. Now, one challenge with any caching solution is always what content should you cache and when should you evict things, or what should you evict. And this, of course, depends on your workload. So if you can predict the future based on your workload, you can use that to make these decisions. But what is of more interest to us today is that it also sometimes depends on hardware. So in particular, the paper that is in this, that talks about this at NSDI, which is a paper called Flash Shield by Eisenman and et al., is about, hey, like, I have this SSD. The problem with SSDs is you have limited write cycles. If you write to them all the time, if you keep writing and deleting objects, that's really bad. So maybe SSDs are a great place to cache something, but you really need to make sure that whatever you cache is not going to be overwritten or deleted very quickly. So how do you do that? So that idea is, hey, use the DRAM as an initial place to cache objects for very short times, and only move objects to SSDs if they're likely to stay in the cache for longer. So one question you might ask is, hey, how the hell do you know what is likely to remain in the cache for a very long time? You don't know the workload a priori. How the hell are you going to predict this? And so in keeping with our times, the answer to this question is, of course, to use machine learning. And in particular, they use SVMs to classify whether objects are likely to live for a short time or a long time. OK, one final problem. So remember our beautiful key value store from before? Well, imagine that a few operations went through, and then the key value system, store went kaput. It's not very good, even if you were sharding. If, say, Lady Gaga's shard went away, lots of people might be sad. How do you deal with this? The answer, of course, is replication. And what replication just means is you have two copies of the data. Now, the main challenge here is how do you maintain those consistency semantics as you have these two copies? So the answer here is that whenever you make any sort, whenever you do any sort of changes that mutate the key value store, for example, this delete, you replicate it to the replica. And you might have to wait for the replica to acknowledge that it has gone through before you can tell the client that things are done. Everyone good so far? Cool. So the problem, again, is you need to keep these replicas consistent. And in particular, you might want to preserve linearizability, which is this guarantee that Hurley and Wing described. It's a very important paper. I highly recommend people read it. But this actually comes down to sort of preserving the order of operations. That's the problem. I can't do many operations at the same time. I need to keep ordering. And this, of course, adds cost because now when the client sends something to the server needs to figure out an ordering, wait for the replicas to apply it in that order, get back a response saying, hey, we've applied, and then respond to them. So the last paper in the session, which is by Park and Ousterhout, talks about the fact that, hey, you can actually solve this problem by having clients, in fact, replicate rather than having the servers replicate. So rather than having this thing where the server acts as a bottleneck and is replicating to many people, the client can be the one that instead sends out all of this replication traffic in parallel. Now, if you think about it, this doesn't work out with the consistency semantics that I mentioned. So they add another little requirement to this, which is you only do this for commutative operations. So commutative operations, in this case, are operations, for example, to different keys, which can apply in any order and don't affect each other. OK, so finally, when you're thinking through these papers, there are some questions that you might want to consider, the main one of which is all of these techniques are rather workload dependent. So if you think about MINOs, it depends on the fact that there is this distribution of sizes, and sizes affect runtime. If you think about Flash Shield, there's this assumption that you can predict future caches. It means, yes, you're using ML, but at some point there are underlying assumptions being made there about the space. And finally, for Pak and Ousterhout, there's this assumption about that commutative operations are relatively common. And even for monoxide, there's this other observation that you can partition in a way that cross-shard transactions in cryptocurrencies are rare. So a question that is always good to think about is, when do these assumptions make sense? Do they make sense for a large set of the workloads that people are talking about? And when are they violated? And what happens? What's the worst case that happens when they're violated? So for example, for some of these papers, when these assumptions are violated, the performance will actually be significantly worse than doing the naive thing today. So it's worth thinking about where the trade-off lies there. And finally, is there a way to solve some of these problems without these assumptions? OK, so that's that. Thanks. So next, we have Akshay, who's going to be talking to us about new networking hardware. Sorry, I forgot as I was speaking.
OK, so yeah, as Panda said, this is the modern networking hardware topic previous session. And if you're lazy like me, one way to figure out what non-modern networking hardware is to look at the list of papers that have been published at NSDI this year. So this is the list of papers. And one question that we can potentially ask about them is, where is this so-called modern networking hardware? And if you look at the titles of the papers, for 3 of the papers, their titles make it pretty clear that the hardware is inside data centers. So data centers are probably something that we want to understand, like the context of networking hardware and how that relates to data centers. So one question that you can ask about data centers is, what do data centers look like? And this is a picture of a Google data center in Iowa that maybe many of you have seen before. And this picture basically tells us that a data center is a big room with some colorful lights and not much else. So what's a different way of looking at a data center? So this picture is a potentially more useful way of describing how a data center might be built. And inside the data center, there are many servers. And each server has some CPU, some memory, maybe some other resources, and a NIC, or network interface card, as we heard before, that it can use to talk to the other servers. And the data center operator connects these servers with this big blue blob called the network, and we'll discuss how that's implemented later. So this is where the first paper, Free Flow, which is by Daehyuk Kim et al., comes into the picture. How should these servers talk to each other? So one paradigm for inter-server communication is RDMA, or Remote Direct Memory Access. So normally, when a server receives some data, the CPU has to do some work to figure out what data it is and where in memory it should put the data. This indirection from the NIC to the CPU to then write to memory can be considered inefficient. So now we have RDMA, which is supposedly better. With RDMA, you buy special NIC hardware, which knows how to talk directly to your memory without involving the CPU. So this has both upsides and downsides. So the CPU, which is slow compared to NIC hardware, doesn't need to spend time processing packets anymore. It can just tell the NIC, when you get some data, here's a piece of memory. Please put the data in this piece of memory, and I'll come back asynchronously and read the data later. So this can be a plus in data centers, where a lot of the time the point is to sell CPU cycles to your customers. So if the CPU is doing less work processing your packets, that's more cycles that you can sell to the customers who are giving you money. On the downside, you now have to buy this special NIC, which involves special hardware and is therefore more complicated. And your applications become harder to write because they have to use a more complicated API. But hey, this paper is in the context of Microsoft's data center. Microsoft has lots of money. They can hire smart people to write RDMA applications. So what does this paper title, Virtual RDMA for Containerized Clouds, mean? So containerized clouds is a fancy way of saying data centers which have servers which run containers. And a container is a way of achieving isolation. So remember that the data center operator makes each of its customers share the resources of the data center. or that each customer, which is leasing a pool of servers, has multiple applications that they want to run on this pool of resources. A container is a way of making it easier to achieve isolation between these different applications by making it seem like the application has a machine to itself. So what type of isolation is this? One way to think about this is that a container is a collection of kernel features that provides isolation of individual resources. So isolation of compute resources with a mechanism called cgroups, or isolation of the file system with a mechanism called chroots, and isolation of the network interfaces that the operating system provides with something called network namespaces. And this last part, the network interface isolation, kind of becomes a problem. We've abstracted away now our fancy RDMA NIC, and free flow is a way of breaking through this abstraction with virtual RDMA networking, which is basically software which is pretending to be this fancy RDMA NIC and is talking to the real RDMA NIC on our behalf. OK, so coming back to this image, one trend in data centers as Moore's law slows down is a shift from running your applications on a CPU to running applications on dedicated special hardware, such as FPGAs. So the FPGA might be attached to your server as the purple box shows in this picture. And one reasonable question that we can ask is, what is an FPGA, or Field Programmable Gate Array? I don't know about you, but when someone says field programmable, I always picture an engineer crouching down during the middle of a picnic trying to debug something. But what this really means is that once in a while, so every few minutes in a modern data center, you can change the FPGA's functionality. The rest of the time, it can only do one prescribed set of operations. The advantage is that it can operate on a large amount of data at once at any given time due to increased parallelism. It's useful to contrast this with the CPU, where it's really easy to change what the CPU is doing. So like every couple nanoseconds or something, the instruction that the CPU is running changes, but it can't operate on as much data at once. So as a result, we can sort of think of a CPU as temporally constrained. It takes more time to process more data. An FPGA, meanwhile, you can think of it as being spatially constrained. You can process as much data in a time that you want, as long as you have enough area on your chip to process that data. So now that we run applications on these FPGAs, one reasonable request is to allow the FPGAs to talk to the other resources in the data center without involving these super slow CPUs. However, CPUs are currently the only entities with the relevant information to enable this communication. So resources are connected to each other using the server's internal network, or PCIe. And this address space is only valid within the scope of that single server. So direct universal access, which is this paper from Microsoft, is a way of specifying a global address space so that the FPGAs don't need to consult CPUs to talk to each other across the network. So now let's come back to discussing how this data center network blue blob is implemented with this paper Stardust, which is by Zilberman et al. So traditionally, data center networks were composed of switches that look like a fat tree. So this type of network was a revolutionary idea a decade ago because each of the switches was identical and could be bought off the shelf. So it's therefore inexpensive to build this type of network. However, what users of the data centers actually want, which I've demonstrated by grabbing a picture of a data center network from a paper last SIGCOMM, is the abstraction of one big switch. So that is, the dream is that servers can communicate across the network, and the only bottlenecks that they run into is when two servers want to talk to the same other server. The data center network architecture on the left, the traditional fat tree architecture, doesn't really get us to this abstraction. There's an entire line of work on load balancing, or deciding how we should route packets along this data center network so that we get as close to the one big switch abstraction as possible. But we can look at how an individual switch is implemented, because an individual switch does actually get us to a one big switch architecture because it is a switch. And individual switches are often made up of several smaller switching chips. And each of these smaller switching chips are interconnected to make the whole thing seem like one big cohesive switch that works as a single entity. So the Stardust paper is basically saying, wait, what if we restructured our network to actually make it look more like one big switch? And the new network hardware idea that is being proposed is an idea called cell switching, which is modern in the sense that it was invented in the 80s. So the idea of cell switching is that it's like packets, except all the packets are the same size, and this lets you play some tricks and become more scalable. OK, so now let's move on to discussing modern network hardware in the public internet with this paper Blink, which is from people at ETH. Remember that the internet is structured as a series of independent autonomous systems, or ASs. So let's say that we are the AS on the left, and packets on an end-to-end path traverse our network before we hand them off to another network for further forwarding. There's a lot of work, because networks fail a lot, in dealing with local failures. So if one of our own switches fails, there's been significant literature and work and effort put into how do we route around this local failure and react to this failure quickly. So here we might notice that one of our switches has failed and route the packets along a different path. However, things become more complicated when the failures are remote or in another AS. So from our perspective, everything worked great. Like, we took these packets in, we forwarded them all the way across our network, we handed them off to some other AS, and that other AS, like, we don't know what happened, like, it probably did its job well. The problem is something has gone wrong in this other AS, and in the worst case, this can lead to something called black holing, where you just keep on handing packets to the other AS, and it keeps on dropping them, and then the end-to-end customers are sad because none of their packets are getting through. So the Blink paper solves this problem with a new piece of network hardware, which is new network hardware because it's implemented in P4, that notices this has happened and corrects for it by making adjustments. And you can listen to their talk for that. So this has been a summary of 4 different approaches or implementations of modern network hardware, and I'm happy to take questions.
It would actually be good to have a few questions. It's late. It's like dinner time or sleep time for some people. I don't know, like, there's people here, maybe you have questions. Really, no one has any questions about any of the talks so far? I know, it always sucks though. Sure, okay.
I don't have millions of dollars to build a data center, so you have to ask the people who do. I think Jay works for Microsoft. You can ask him.
Okay, it's me again. Not for the last time this night, but this is the last time I'll have slides. After this, I'll mostly just be introducing people. So this is the next session, which is about analytics. And this is like a session that I think lots of people know about. There was a lot of interest in these sorts of things. So, but still, let's look at what's there here. So like computers have always been about analyzing data. That was what the government was paying for in the 50s when all of this was coming around. So the difference was that at some time in the 2000s, we decided that everyone should be able to analyze lots of data quickly. And what allowed for this was we had frameworks that simplify processing of lots of data. You can see examples on the right. We suddenly had easy and quick access to large amounts of compute and storage capacity. So this happened with things like AWS and Azure, and also with things like OpenStack and Kubernetes. Like now this seems commonplace. A decade ago, this was not something that I could have imagined. The cloud was some weird mystical thing that I saw on posters around the Microsoft campus. And finally, we had people who decided that you got value from processing large amounts of data. And this last bit is important because this is what pays for a lot of this shit. So obviously, this has been around for nearly 6 or 7 years or 8 years. My entire time in grad school, this was the big thing. So the question then is, what has changed? Why do we still have talks on this stuff? Well, the thing is, these things keep changing, and there are 3 kinds of changes that we've seen that are interesting right now. So the first is the abstractions for sharing resources have been changing. We used to largely do these with VMs that were allocated at fairly large temporal granularity. So you got a VM for an hour. Now suddenly we have lots of fine-grained allocations happening. And you might want frameworks to change to take advantage of these. The cloud providers have seen increased demands, and so they've been increasing the number of machines they have in their fleet, so they need to manage these machines better. And finally, we have new types of data and new types of analysis that, again, feed into why people are getting value out of doing this sort of work. So I'm going to go through through these three topics. Each of them has a paper associated with it. So I'm mostly going to just focus on what that paper needs and nothing else. So let's start with the new abstraction bit. So there have been many new abstractions in the last few years. The one that I'm going to focus on here is serverless computing. So serverless computing is this thing that cloud providers, I guess starting with AWS, but now everyone started providing as a way to launch relatively small jobs that lasted for short durations of time really quickly, where really quickly here is relative. It can be between a second and a few milliseconds, but still, pretty quickly. And the only thing you needed to pay to get this was you needed to agree that your job will end in some fixed duration of time, which used to be 5 minutes, is now 15 minutes, keeps growing every day. Now, there were lots of technical changes on the provider side that allowed this to happen. We had things like containers. We had faster VM launches. This is something that there were several papers on at NSDI and OSDI, which people seem to have adopted those similar techniques. But now that we have this, how do we get analytics jobs to take advantage of this super fast launch? And this is particularly important because these things weren't designed for that. They were designed for more front-end jobs. Like I receive a web request, I build out a web page, I send it back. I don't need to have a web server all the time. So in answering this question, we need to ask two questions. Why do you want to run analytics on this environment that probably wasn't designed for it? And how do you do it? So in terms of why, the main argument has been that spinning up and maintaining a cluster is really difficult for most people. And this is the story of my grad school career working with Jan. So I worked with Jan and with Scott. And whenever I worked with Jan, Jan would always ask us to spin up 100 machines. 96 or 97 of them would come up. The other 3 wouldn't. And then you banged your head against the wall until you figured out how to bring them up. Also, sometimes people like me forgot to shut down, and then you ended up with like $40,000 bills, and that was not fun. So yeah, this makes it easier to run. In terms of how you use it, well, what you do is you build a new framework, because that's the cool way to do things. And one example of such a framework is Pyren that came out of Berkeley a couple of years ago. So we already have a framework, and we have some reasons why. The challenge, though, is that remember how serverless wasn't designed for analytics? One of the things that they didn't design it for was for these serverless functions, these things that you're running in a serverless platform to communicate with each other. Why would you need to communicate? You're just generating a web page. The problem is that when you do something like data analytics, it's essential. How do you sort items without communicating? Like, hey, I see 500 items, you see 500 items. We're supposed to put them in some order. How the hell do we do that without knowing where things are? So the way people have solved this so far is by having them read and write to shared storage. So S3 or Azure's Blob Store or Google's Blob Store. The problem is this can be really slow. Like this writing to the storage is where you spend all of your time. You're not doing anything super useful for a lot of it. So the first paper, which is by Shifan, Sivaraman, and Jan, tries to address this problem. And their technique for addressing it, is use a faster key value store that's running on a VM, which, by the way, all of these data centers still provide, and use that for a lot of the communication. OK, so go to their session. They'll talk more about how exactly to use this most efficiently. But as you're doing this, one question to consider is this an ad hoc solution? Could we imagine designing storage that maybe the cloud providers use that are specific to this? And would we make different decisions from what these authors did, where they were trying to adopt this and run it in current cloud environments? So in particular, are key value stores like Redis the right way to do this? The second question is, does this negate some of the simplicity and the benefits of serverless that I was espousing? Right? Now, sure, I am only running one machine, but if I forget to shut it down, eventually I'll still get a $40,000 bill, and someone would still be mad at me. And finally, is this general? Are there other things like this that we'll need to build to use serverless here? So consider something like graph processing. There's a lot more communication, a lot of different communication. How do you do that? OK. So that was one. The second one is we have these larger fleets with new requirements. So, OK. We have more machines. This is not surprising. People earn money by selling machines. They buy more machines so they can make more money. We also have new abstractions. We have serverless, which we just talked about, and containers. So the actual utilization of machines is changing much more quickly than it did in the past. In the past, people were running machines for entire days and not taking them offline. Now they might be taking them on and off all the time. So scalability becomes a challenge for cluster management. And to see this, consider this cluster manager. And so we have a set of 4 machines. The red squares indicate resources that are in use. Now, this cluster manager gets a job that's looking for 3 resources spread across 3 different machines. So vertical lines represent different machines. The boxes represent resource requirements. This is simple. I can just, sorry, oops. OK, first you receive one where you want 3 resources on the same machine. Then you receive this one where you want 3 resources on different machines. If you try to satisfy these on the basis of arrival, the first one you can satisfy by just placing the empty boxes. The second one you're kind of stuck on because you don't have any resources. The third one arrives. Well, there is space to place it, so you place that. But now you're still waiting on job 1. And wait, oh, things just cleared up because jobs exited the system, and now you can place this. The thing to note here is not that this is a hard problem, but the fact that that stupid cluster manager is constantly sitting there trying to figure out, hey, what's in use, what's not in use, what can I place, what can I not place? And as you start scaling this up, that's a lot of dynamics for it to account for. So it requires tracking these sorts of things and merging this behavior together. And of course, as number of machines grow, this becomes harder to track. So the question is, how do you get past the scalability problem? So there's, of course, many possible answers. But the answer that Microsoft picked in Hydra, which is the paper that's at NSDI, is quite simple. They chose to use sharding, which, remember, we spoke about in my previous talk. So we're not going to talk about that. But this is something that has been deployed within Microsoft. So the paper actually talks about some deployment experiences which might be interesting to people working in this area. Some questions you might want to consider is, what happens if you have policies that span multiple of these shards? So for example, I have a policy about number of machines that I can allocate at a time. So this is the same question that cross-shard things have in general. Could you have things where jobs trigger other jobs? And in that case, how does placement work? And finally, what is the granularity of a job that you're assigning to a shard? OK, so the final bit is new workloads. I have very little on this. So workloads that you use, of course, depend on what you want to do. The particular workload that this NSDI paper called DShark looks at is how do you analyze packet traces. The reason packet traces are important is that they provide a way for you to quickly detect and diagnose problems in data centers. The question has always been, how do you process all of the packets going through a data center? That's a lot of data. And we'll hear more about this in other talks tonight and in other sessions tomorrow. So there's been lots of attempts at doing this, but people end up doing this very ad hoc. So DShark is this new proposed framework for specifically looking at packet traces. And just go to the talk. That'll tell you more than I can. Cool. Questions while I look up who the next speaker is? Oh, actually, yeah. The next speaker is Anirudh, who's going to be talking about data center networks. But if you have questions, I can still answer them while he comes up. My talk so clear.
Except I have a question.
Excellent, please.
Yeah, so Nadir from UBC. The first talk you said the serverless is aware of VM. Do you assume that serverless and VM are co-located in the same region, same? Yes. Okay.
So I'm not the author of that paper, but yes,
it's
that
always
paper does assume that.
Always co-located. Okay.
Well, so far we do not have examples where they're not co-located. I think when that day arrives, there will be other interesting questions about what happens when they're not co-located. But currently, it seems a bit strange to make that decision just because you're using the same hardware.
Good, thanks.
Just connect. I don't. Does anyone have a mini DisplayPort adapter from HDMI? Thank you. Sorry. Yes, this should work.
Yeah, thank you. Oh, okay. Hello? Yeah.
Definitely on the mic. I'm going to steal my mic.
Okay. Okay, so I'm Anirudh. I was kind of drafted into doing this session because Jeff Mogul couldn't show up. So I'm trying to do the best that I can on a topic that I'm relatively unfamiliar with. So any questions can be redirected to Jeff. Okay, so what's this session about? One way to look at the session is to look at the words in the title. So it's about data centers, which I think Akshay pointed out. They're these large building scale collections of computers that power a bunch of things today, cloud computing, internet applications, and such. Okay. It seems a little redundant at NSDI, but the network is basically the infrastructure of the hardware and software that powers this data center. And architecture is this big picture view of the data center network that studies the design of the network as a whole without worrying about the individual aspects of, say, a particular load balancing algorithm or a particular congestion control algorithm. So these three are all sort of big picture papers in that sense. Okay. So the important thing with any kind of architecture is what goal it's trying to address. So what are the kinds of goals you might care about from a network? Specifically in a data center, you might care about high capacity, specifically high bisection bandwidth. So if you took the graph representing the network, sort of cut it in half and measured the capacity flowing across the cut, you want that to be as high as possible. You might want it to be fault tolerant. You probably definitely want it to be fault tolerant for many definitions of faults. You want it to be cost effective. You might want the components to be readily available. So there's a bunch of different goals that you might care about, and these are all things that people have thought about when designing data center networks. But more to the point, what network goals do these papers care about? Okay, so there are three data center network architecture papers here. The first one is this system called Shoal by Vishal Srivastav and others. And the goal there is a low power network where the network infrastructure consumes as few watts as possible and really predictable low latency. So they don't want like the tails to be much higher than the median, for instance. And their guiding use case is this context of a disaggregated data center. We'll talk about what that is. So that's the goal of the first paper. The second one by Shizhen Zhao and others, this is a paper from Google. And the goal here is to build a network that is easy to expand live. Like while applications are using the network, you want to be able to expand it with more capacity, or maybe change the internal topology of the network without disruption. We'll talk about how they do that. And the last paper by Mingyang Zhang et al. It's a collaboration between USC and VMware. This paper tries to put a framework around how hard it is to manage a network throughout its lifetime, both when it's set up and when it's in this ongoing process of being managed. And as a side effect, they come up with this network topology that explicitly optimizes for this goal of low management complexity as defined by them. So these are the sort of three papers in this session. Okay, so some background on data centers. Some of this is repetitive. But just to give you a sense of scale, these are the latest numbers I could pull up. Of course, this varies depending on the particular data center. They're typically characterized by custom software and recently hardware as well. And the topologies are optimized, as I said earlier, a few slides ago, for high bisection bandwidth and rapid failure recovery. So here's a one-slide overview of the topology. This borrows from an idea from the telephone networks called Clo networks. This is quite old at this point, where the idea was to build these large telephone exchanges out of smaller cross-point switches. And In the context of a network, the idea is to try and approximate a large port count switch using smaller port count switches that are available. So here's what I think is the simplest illustration of that. Let's say you have switches with port count 4. You take 2 of them, arrange them in one layer, take 4 such 4-port switches, arrange them in the next layer. Connect all ports on top with half of the ports on the bottom. That frees up half the ports on the bottom. And you connect servers to the ports at the bottom. And these things have names. Those are spine switches, leaf switches, and those are just servers. So in general, for a k-port switch, you basically leave k over 2 for servers on each of the k-port switches. So in general, you get k square over 2 switches for a 2-layer topology. And the neat thing about this idea is you can sort of recursively apply it to more layers. So you can do k cube over 4, k power 4 over 8, and so on. So typically, data center networks have 3 or 4 layers. Okay. So that's the topology as a primer. And here's what they do for congestion control and load balancing. And these are relevant because some of these papers touch on aspects of each of these things. So for congestion control, pretty much all of these data centers rely on some form of switch support to mark packets when packets going through the network encounter a large queue. Again, this idea is quite old. It goes back to at least 88, but it's sort of been recast since the early 2010s. By DCTCP. Then there's this question of how you spread load between the leaf and the spine links, or more generally between one layer and the next. And you do the simplest thing there. You take a flow and assign it to one of those links at random. Again, this is an old idea, but in a new context. And the last decade or so has seen considerable research on all 3 topics: congestion control, load balancing, and topology. So that's sort of the context for these papers. Okay, so the Scholl paper, the problem it tries to tackle is the rise of disaggregated computing, where you take memory and compute that were historically on the same server machine and sort of rip them apart and turn them into independent hardware nodes. There's a bunch of benefits to this. You can treat the entire sum of all the memory in the cluster as one resource without worrying about, hey, this particular machine has some memory, there's no job running on it, so that memory is stranded and can't be used. And theoretically, you can pair up any compute node with any memory node, and you don't have to sort of couple the evolution of memory and compute. And in principle, you can extend this to other kinds of hardware. Now, the workhorse for disaggregation is the network, right? If you want any compute node to be able to talk to any memory node, you're essentially treating that as the interconnect within a computer. So you're doing, in effect, what is going on inside one of your multi-core chips, but at the level of a data center. Okay? And the benefit of this is you don't strand resources and such. So Scholl focuses on the design of this network. And for now, it targets rack scale disaggregation with a few hundreds of nodes, not like a few hundred thousands of nodes. And the architectural goals are low power, because they don't want the network infrastructure to add too much to the power consumption of the rack, and predictable latency. This is a really high-level summary of the design. Their core idea is to use circuit switching instead of packet switching. And this frees up a whole bunch of space on the switch, which is typically dedicated to things like packet buffers, so the memory consumption goes down drastically. And they use this sort of static schedule that periodically connects every rack node to every other node. So scheduling is really, really simple, makes it amenable to a hardware implementation. Here's a customary picture from the paper. And they use a bunch of these ideas. So these ideas by themselves aren't new, but they put them together in a nice way. And in trace-driven simulations, it shows benefits relative to a bunch of existing protocols. So the things to think about when reading this paper or attending the talk is, how do you take existing applications like, say, Spark or Hadoop or MapReduce and port it to run on Shoal, because they use their own custom network of circuit switches, custom NICs, and so on. So the second paper is about live network expansion. It starts off with this premise that it's difficult, or it's considered difficult, to support expansion in flow networks without disrupting live traffic. In fact, there's been a bunch of prior efforts that have explicitly taken this as a starting point and come up with new topologies that are more amenable to expansion. And this work, which is in production at Google, shows that it's possible to expand flow networks incrementally. And the thing that I learned from this paper is this idea of a patch panel, where instead of connecting servers to spines directly, they use this idea of a patch panel. Anyway, it's probably not clear from the figure, but it's basically this sort of interconnection point where the servers are connected to the interconnection point and the spine is connected to the interconnection point. But you can sort of reconfigure the connectivity just by playing around with the patch panel. So the physical topology is how the servers and spine blocks are plugged into the patch panel when it's first deployed. The logical topology allows the server to spine block connectivity to be reconfigured dynamically. So that, okay, I guess that yellow line, which is barely visible, is one example of that connectivity. So the paper essentially comes up with this nice integer linear program formulation for figuring out which yellow lines should be connected with each other. And they want to minimize the number of such rewirings so that they don't have to burden the operators too much within the constraints of the physical topology. And at data center scale, it turns out that treating each of those server and spine blocks independently turns out to be unscalable, so they group a bunch of blocks together and solve the ILP with the same outcome for groups of blocks. It also turns out they don't know what is the right kind of aggregation to use, so they do the dumbest thing possible, which is you run multiple aggregation strategies in parallel and pick the simplest solution, because Google isn't particularly starved for compute. So the thing that I was left wondering at the end of this paper was, how often does the logical topology change versus the physical topology itself? Like, the paper makes this argument that the connectivity to the patch panel is a one-time thing, but then the connectivity within the patch panel changes. But there weren't, to me, use cases presented that show that you keep changing the logical topology frequently. So this last paper tries to put a formal framework around what it means to manage a network and what makes it complex. And the happy side effect of doing this is that there's a class of topologies that is better at being managed than existing topologies on the metrics that they define. So what are these metrics? These are somewhat natural metrics. So these are metrics that are relevant at deployment: the number of switches, number of cables, number of panels. They have this interesting concept of a bundle type, which is basically a tuple corresponding to the aggregate capacity of the wire and the length of the wire. So this corresponds to the distinct number of cable types that they need to order or maintain in their inventory. And then they talk about these incremental expansion metrics that show up during the lifetime of the network, which is number of expansion steps for the topology to be evolved from one configuration to another, and the average number of rewired links during an upgrade, and so on. So they find that the CLO topology is better than Jellyfish, which is a research project that basically builds these data center networks out of random graphs. It this paper finds that CLO topologies are better on deployment metrics, but are actually worse on expansion metrics. And that's consistent with how Jellyfish was motivated in the first place. And the final finding of this paper is this class of topologies called the fat clique that gives you both. And essentially, the idea is to use a hierarchy of cliques. So the clique idea is basically a bunch of nodes that are all connected to each other, similar to the random graph idea from Jellyfish. And that gives you the ability to expand. But they also have this hierarchy which lowers wiring complexity. Okay. So they have a clique of switches, and then they have a clique of sub blocks, and then they have a clique of blocks. So there's basically cliques at every level. And these are sort of connected hierarchically. The one thing to think about, which this paper doesn't address in too much detail, is they talk about all of these management metrics, but it's unclear how fat clique compares to, say, CLO or Jellyfish kind of topologies on performance. So yeah, that's about it.
Hello. Presume I am audible. Hello, everyone. Hi. Yeah. So let me bring you to the wireless session. And my goal here is to give you some basics so that we can appreciate the work that has been done in the wireless session, right? It's going to be an amazing session. You don't need coffee to wake up. So just come there. It's an early morning, right? And you'll wake up by just listening to the talks. So let me get started, right? There are 4 fundamental questions the wireless session is going to answer, right? And probably the questions even doesn't make sense right now as I put them out, right? And therefore, I'm going to do a simple thing, which is what I'm give you a basic concepts, right? As to what you really need to know so that we can understand these questions and then understand their answer to these questions given by these papers, okay? So I'm just rough outline, right? I'm going to go over wireless spectrum, how wide it is and so amazing it is, and basic communication architecture and how people came up with MIMO, and then in recent backscatter communication. So this cocktail I have created specifically to understand this session better, okay? And this cocktail is sufficient for you to like really get the gist of all the talks. So let's look at wireless spectrum, okay? So wireless spectrum, as we all know, supports wide variety of applications, right? And in recent times, at least, I also did some work where some people just were monitoring wireless spectrum, and they heard some walkie-talkie communication, right? It was totally unencrypted, right? And doctors saying this patient is going for hernia operation or something like that, right? It just was amazing, and some paper published this study, right? So the point I'm trying to make is that first, the wireless spectrum is wide. It covers the entire 6 gigahertz. A lot of it is unencrypted. You wouldn't even realize how much of it is unencrypted, right? And you can really get tons of information by just looking at it, okay? So one of the paper is going to try to look at it, right? And now let's understand, so this wireless spectrum, right? How do we use it today, right? So the way we use this wireless spectrum is that, so the way to do is that, let's say if I asked you if you want to communicate at a frequency XYZ, right? What you could do is you could generate a signal at that X frequency, right? And transmit it, right? Instead of doing that, what wireless radio designers came up with is a very interesting architecture. They decided like we're going to generate signals in a baseband, right? And then going to upconvert it and send it at those frequencies, right? Okay. And let's let's just give you a sense of it, right? This is what you do. At transmitter, you generate this signal at near close to DC, x-axis is frequency here, and then you shift the frequency at any arbitrary frequency you like and transmit it, right? And the other side does the reverse of it to receive that signal, right? Okay. So now we understand this, right? Let me just give you a quick architecture breakdown of how this is done, right? So even if you had to send an on-off signal, right? You create a digital on-off signal, pass it through your DAC, right? You get an on-off signal, right? Then you pass it through this component called mixer, right? What it really does is that it multiplies your signal with a sinusoid and takes it to the desired frequency you like, FC, okay? And once you go to this frequency, you do a bunch of basic operation, you amplify it, which is done with this PA, something called PA, labeled here, and then you transmit it, right? And the receiver receives it. It has a low noise amplifier, okay? And then it does the reverse operation. It takes that frequency FC, brings it back to the DC, and then passes it through your ADC and decodes the signal, right? Easy, okay? One of the papers is going to show a radio or receiver architecture. Therefore, you need to know exactly how radios work, right? So now that we understand how radios work, how communication work, right? What did wireless people did next is that, look, frequency is short. We keep asking for newer and newer spectrum, right? We put billions of dollars in buying new spectrum, right? So some people, before they started putting billions of dollars, they realized, why not scale up, right? Why not reuse the same frequency over and over again, right? So they came up with something called MIMO. What it really means is that you just keep putting transmitting antennas, right? Now, one might ask, why not just increase the transmit power, right? Just blow it out to the highest, right? And just get as much as data rate you want, right? The one component which is different with MIMO is that you can send 2 different streams with MIMOs, right? And also, FCC put some limitation on maximum power you can transmit, right? So by putting multiple antennas, you can do 2 things. One, you can increase the range of the communication by doing some kind of a nice beamforming, right, towards a particular receiver, right? 2, if you put multiple antennas on the receiver side, right, now what you have is you have a system of linear equations between transmitter and receiver. And you can use this to get multiple data streams across, right? So what did MIMO provide you with? It can provide you with range and capacity improvement, okay? And one of the papers is going to show that what wireless designer came up with doesn't really work in the MIMO capacity gains. And they're going to show a way how to scale up capacity, right? Now, here are the things which you really need for MIMO to work, okay? First, your transmitter needs to have phase and frequency synchronized to transmit signals so that they can be constructively added at the receiver or destructively added depending upon the application you're looking for, okay? And then they further needs to be time synchronized, right? Even if you are distributed or co-located, you need to achieve these properties to get MIMO's gains, okay? Now, on the other side, to increase throughput, right, what is one rule of thumb? The one rule of thumb you need to think about MIMO is following, okay? The number of paths from transmitter to receiver you have, those are the number of spatial streams you would get, right? So what it really means is that when you're transmitting multiple streams, you need your channel to have as many paths as it can take. That would increase the number of data stream or the number of data, amount of data you can send from transmitter to receiver, right? So again, this paper, now there are 2 papers we're going to use this concept, right? And probably this is good to understand now, right? So there is like a distributed MIMO concept which I have introduced, right? And how does data rate scales up, okay? Now, there was an era of IoT came, right? And we started doing low power communication, right? And there has been low power communication for like at least 2 decades, which is most popularly known as RFIDs, right? What was these RFIDs great? First of all, RFIDs were invented by a mechanical engineer, okay? Not by an electrical engineer, not by computer scientists either. He was just trying to tag a bunch of objects and really track them, okay? He was starting with very simple thing, right? And his goal was following. Today's transmitter and receiver just abstracted out as very simple model, right? You take the baseband signal, you upconvert, and then you amplify and you transmit, right? And what is the problem with today's transmitter? They blow out power like hell, right? We keep turning off Wi-Fi on our phone to save the phone's battery, right? So what can we do to fix this situation, right? So this person, okay, let's say we were just trying to do on-off communication, we still needs this kind of entire complex architecture, right? So this person looked at a very simple idea, right? Which is backscatter communication. What is backscatter communication? Let's say if I had a light, and if I put a mirror, and if I keep moving this mirror from reflect to non-reflect position, right? I create communication, right? And it's just a mirror. It's passive. It doesn't even require any power, right? So backscatter guys realized, can we do the same for wireless, right? And they came up with this new architecture. Look at on the right, the tag. It has a single transistor, right? Barely consumes any power. And even this device is powered by the backscatter signal or the actual RF signal, right? The way it works is that you send a RF signal to the tag, the backscatter tag. It reflects it back, like on-off. And it requires less than a few microwatts to toggle it. Furthermore, it is also you wake it up by sending an RF signal to it, okay? So you do it, you basically wake this tag up, and you get data back from it. Now, one of the papers is going to deal with it, right? So now two of the papers are actually going to help you understand how to improve backscatter, right? Now, to get a little bit of mindset of backscatter, right? What are the problems with the backscatter? Let me just list them, right? First, range. Now, these backscatter devices, if you're planning to power them up with the RF signal, you cannot put them farther away from the transmitter, right? That's one of the biggest limitations for RF IDs, right? Their range is limited to 5 to 15 meters. And that's because you cannot power them up, okay? And one other idea one can think of is that let's put multiple transmitters, right? There's already multiple transmitters out there in the environment, right? And you realize that if these multiple transmitters, if they are uncoordinated, right? Remember the concept of MIMO, right? If you have multiple access points, and if they are not coordinated, their power won't add up constructively, right? Therefore, you won't get range increase, right? Or furthermore, you will cause more interference in the case of backscatter scenario, right? So that's one challenge with the range, right? Now let's look at capacity, network capacity, right? One of the biggest thing which Amazons and other factory infrastructure people care about is how can I read thousands and thousands of a tag in a particular environment, right? At a very fast rate. What it means is that able to talk to multiple nodes, right? How does medium access control scales up? And now, remember, these devices, right, are extremely dumb. They need to even send a signal to wake them up, right? Now, they cannot hear each other. So CSMA MAC, right, which we use for Wi-Fi extensively, where we just shut off whenever somebody else is transmitting, wouldn't even work. These devices needs to be sent a signal to just wake them up, right? So once they start shouting, they don't hear anybody else. They just keep interfering with each other. Further, this results into an additional complexity on the access point side, right? Access point side needs to be extremely, extremely smart to be able to scale up to thousands of tags at the same time, right? And then people started coming up with these new physical layer mechanisms where even when multiple tags are backscattering, you can still decode them. It's called code division multiple access, CDMA, a very popular technique in 95s, which we dropped in 2000 and went to OFDM, right? So let me now come back to this question, right? Okay. Can we push the range of backscatter communication using distributed MIMO? I think hopefully the question is now extremely or clearer, much clearer, right? So let me just ask and answer these questions one at a time, right? So the first paper probably you're going to hear is about how are you going to use distributed MIMO to increase the range of the backscatter tags, right? Remember, the range is proportional to the distance at which it can be woken up, right? So what is the idea? The idea is following. We're going to go from the left side, where you use multiple co-located antennas to create directional beam, to the right, where you have 4 antennas, and still they are able to create as strong signals and distributed in the space, okay? What's great about it, it covers much more area with the same number of antennas, okay? And this paper is going to demonstrate how you can build this algorithm, right? Now, why does distributed MIMO changes? Distributed MIMO has been studied for doing Wi-Fi communication, right? The problem is these tags are dumb, okay? They cannot give you any feedback so that you can create some kind of a constructive pattern to wake up the tags, right? And this paper is going to deal about that as well, right? So distributed MIMO is extremely challenging, right? And again, I'm not going to give you any more insights on this. Attend the talk, and let us give a chance to the authors to explain us why that's a problem, right? Now, on the next problem, right, remember I said backscatter networks have a big problem. You want to read thousands of them simultaneously, right? Okay, and there is a paper which will going to show how we can do that, right? And the key idea this paper is following, right? This is one of the possible communication methodology where they use the slope of the frequency and its shift to communicate 0 and 1. For example, if you keep looking at it, it's continuously shifting and it's sending some 4 QPSK data, right? Instead, what this paper says is that every one of these tags, let them backscatter all simultaneously. And on top of that, it puts an on-off coding. So the idea here is basically you have these lines appearing and disappearing. And that's the mode of communication. And the line itself is representing the tag or the identity of the tag, okay? And this paper will hopefully explain how they can help scale the backscatter networks to 256 tags. It combines 2 of the classical CDMA technologies, chirp spread spectrum, right? Just think of them as adjectives, right? And then there is something called code division multiple access, which we kind of know of. And they're going to use on-off based code division multiple access. Okay. Now let's come to the third paper, right? It's a very interesting paper, right? Remember I told you there is a corollary, right? Number of paths you have is equal to the number of spatial stream you can get in MIMO, right? And this paper decided, let's increase the number of paths, okay? They built a reflector, a passive reflector, which consists of thousands of backscatter antennas, well, not 1,000, but 36 backscatter antennas, right? To show how you can create constructive paths or additional paths which can increase MIMO's throughput as well, okay? It's like programming your environment, right? To be better MIMO capacity deliverer. Finally, this work which tries to sense entire 5 gigahertz in 5 milliseconds, right? So now just to give you a sense, right? If you can do this, right? Remember I told you wireless spectrum has tons of information, right? This can skim through all of that information and give you statistics about what's going on, who's talking what, right? Really, it can be the next NSA, right? And it can be fit in your phone, right? Low cost. So the fundamental idea which this paper brings in is following. So the way today's receiver works, right? As you remember, right? There is a local oscillator which brings down the frequency, right? So to set this local oscillator, you program it, and it takes a couple of milliseconds to get to that frequency. So these guys said, let's not program it anymore, right? We're just going to ask it to continuously keep changing frequency and keep increasing. The figure on the right shows it, right? What they're doing. And while they're doing it, they capture some small amount of data for every one of these bands, and they are able to make inferences based on that, right? So hope I have given you a great insight as to why attend wireless session. Thank you. Questions, feel free to raise them.
Okay, while people are asking Dinesh questions, next we'll sort of we'll sort of deviate a bit from the sessions, and we'll have Costin talk about network modeling, which is one of the sessions on Thursday.
Hey everyone, I'm Kostin from the Polytechnic of Bucharest. Sorry for disrupting the order a bit. I'm slightly jet lagged. I just landed today, so if I waited until the actual order, I'd be sleeping in the back there, so you're probably useless. All right, so I'm not sure I'm going to be able to match Dinesh's energy, but I'll try. All right, so this session is on Thursday, it's the next to last session, and it's about network modeling. So basically, this is all about network verification and the fact that you can't really do network verification on the actual software that you want to verify in most cases. All right, so if you look at what an admin or a programmer, the job of an admin, basically looks like something like this. Either the admin writes some configuration files or writes some sort of P4 program or some SDN controller. And then it has some sort of policy that it has to obey, okay? So the policy can be implicit, like, the DIN is important, has to have connectivity, or, something else. And then basically what network verification does, more or less all the approaches to verification, they take the following step. They start from this input, which is either a configuration or some sort of program, and they don't verify that thing directly. They turn it into a model. And then they take the model and they check it against a formalized version of what the admin is after, some sort of policy that's expressed in machine-readable language. And then there's a verification tool that basically uses formal methods to make sure that the policy and the model agree. So this is a very general, very general slide here. So the config/program could be either a traditional, fixed function router or switch, in which case you'll get a fib out of it, and then you take the fib and you translate it to something that you can reason about. Or you can have a programmable switch, which is a P4 program, or you can think about a middle box implemented in C, right? And that could be either stateless, in which case it's easier to verify, right? Or it could be stateful, in which case it's actually very, very difficult to verify, right? And actually deriving the data plane model from the code you're trying to verify is either automated, and this is the case for stateless stuff, traditional fibs, P4 programs and stuff, and it's manual for stateful stuff. So we don't actually, or we didn't actually know before this NSDI how to do it automatically. So as I said, deriving data plane models, every tool out there, every verification tool has its own language to describe data plane model. And I'm not going to discuss all of them. Basically, there's a reason why there's so many of them, because they differ in how expressive they are and what they can express in terms of data plane functionality, right? So for instance, if you start at the top, that's the most scalable one, and it's very limited in what it can express, and you can check it very quickly, and then if you go down, it basically gets more and more difficult. But the biggest problem that all verification tools have is that there's this gap between what you're trying to verify, which is data plane, and what you're actually verifying, which is the model, right? And that's a problem that we somehow have to address if you want to have accurate results. And so this is the model. The other side is the policy, right? So you have roughly two types of policies. You either have isolation and reachability policies, which are very easy to express, but they don't really cover everything that a network is supposed to do, right? So think about a P4 program. If you want to specify what a P4 program does by saying what should get through and should not get through that program, that's a very sort of weak specification, because the P4 program could change the packets in many, many ways. And if a packet makes it through, it doesn't mean the program is correct. So to solve this problem and to be more precise, you could use formal languages, but that's actually very difficult to use for like a normal administrator or a normal programmer. So the problem with specifications, as soon as you go from natural language to something that you want to be exact, you either get an incomplete specification or something that's actually very difficult to express if you want to capture all cases. Okay. So the holy grail of network verification is the following. It's like, what you would really like is to actually verify the data plane code, whatever the data plane is, right? You take the implementation of the TCAM, if that's a fixed function router, or the C code, or whatever. And ideally, you would like the policy to be, well, so self-explicit that you don't need any input from the admin, right? So ideally, you want to have to check something that's obvious that should always hold so that you don't require the administrator to tell you exactly what it wants, because that's actually very difficult and you can get it wrong and so forth. And actually, all 3 papers in the network modeling session try to move towards this goal. And they do it in completely different ways. So the first paper is actually a paper coming from my group in Bucharest, and basically it tries to make it easier to write policies. And the key idea is that instead of actually specifying the policy you're after, you specify 2 data planes that should behave similarly, and then you just check that, right? So basically, the paper says you can use equivalence as a way of testing that 2 things well, you can test equivalence between 2 things to check whether there are any problems in your data planes. And the example I'm giving here is this tenant cloud interface that I have on the top. This would be, for instance, what you get in Amazon EC2, or if you use this software called OpenStack. And this is what the tenant does to create LANs and to interconnect them via routers and so forth. And this is basically the logical configuration of the network. And it's sort of easy to understand what it does. It's pretty obvious. We all know what a LAN is supposed to do, what packets get and don't get there, how packets are modified, what a router does and so forth. But then what the cloud does, it takes this specification and actually runs it through a networking driver and outputs a list of actual network configurations, fibs, ACLs, rules that get installed into the actual network that are supposed to collectively behave as specified by the sort of high-level thing. And these 2 must be equivalent, right? So this is one example where you might use this primitive, all right? So the paper presents this tool that's called NetDiff. Basically, it's built on top of prior work. And the input is 2 data planes written in this language that was presented previously. And it basically says for these data planes, I want that injecting packets on these 2 ports should result in the same packet going out, right? And the way it does this is by using a technique called symbolic execution. You can think about symbolic execution as a way of enumerating all possible inputs to a program in a much more scalable way than actually trying all possible inputs, right? So intuitively, if these are all the possible packets you could put in program 1, then basically symbolic execution finds some equivalence classes, and in each equivalence class, then the packets will be treated in the same way. And then basically you just take each of these equivalent classes and you put them in the second program, and you make sure that the outputs sort of agree. And I won't go into details. All right, so that's the idea. And basically, the paper applies this to checking whether updates in a live network preserve the behavior of the network in terms of routing, to check if 2 versions of a P4 program behave the same way. So you might want to change the order of table applications and so forth. You want to check the big switch assumption that was mentioned earlier. So basically, I think the paper takes one of these mininet models of a fat tree network and just checks it against a model of a big switch. And finally, it looks at OpenStack Neutron and finds some interesting bugs there. All right, so the second paper does not look at policy. It looks at this very tough problem of verifying middle boxes written in C or in any other Turing-complete programming language. And it looks at middle boxes that keep per flow state, right? So as I mentioned earlier, currently we don't have a good solution in generating models for these middle boxes. And the paper is called Alembic. So it tries to create models of stateful network functions to be used in network verification, and it tries to do it in an automated way. The status quo is people just write manually crafted models of these network functions. The reason for writing these models is because you have to simplify the thing that you're trying to model, otherwise the verification won't work, right? So that's why people write manual models. And the approach they take is actually a very, very bold one. They not even look at the source code of the mailbox of the network function. They try to figure out what the network function is doing just by injecting packets into it and looking at the results, right? And the tool is called Alembic, and basically the inputs are a binary of the network function that is under test, so that you're trying to model. A configuration schema, so what type of config rules this network function accepts, and this is what decides, what types of model you build, right? So basically, you need to clearly specify what configuration parameters you have, and this will drive the testing. A list of network interfaces and what packet types the network function accepts, and this is the inputs that the tool will try to inject into the network function. And at a very, very rough approximation, it goes about building a model in the following way. So first of all, it tries to consider each rule in the configuration file separately. When I say a rule, think about a single IP tables rule, right? For this specific source address, drop. For this specific destination address, allow. For this specific network mask, NAT, right? So this is what a rule means, okay? So basically, this tool, to get scalability, it will try to figure out what each rule is supposed to do and how each rule processes the packet, processes each connection, and then it will compose these rules after figuring out the per rule state machines. And then within a single rule, you might have an entire range of addresses that can be applied. And again, the assumption here is that any single connection will be treated in the same way, and basically what the tool does is actually just tries to infer the state for a single connection and then extrapolates that the same rule will hold for any possible connection within that range. All right, so there's some more details, but the crux of the tool is they use this finite state machine model. So they derive a finite state machine model of the middle box under test by using the L-star algorithm, which is a classical algorithm developed by Anglo in 1983, I think. So, and the cool part of the paper is that they are really the first ones to attempt to do this very difficult problem, and they're actually pretty successful at it. I mean, the paper comes with a long list of limitations. So it only looks at TCP, SYN, SYNAC, and a few other types of packets. It only tracks very simple changes to the packet headers, but still it's actually quite nice. So the evaluation, they looked at a bunch of network functions, and these are the ones they looked at. The worst case runtime is tens of hours, but they say you do it only once, and then you can reuse the model as many times as you want. And basically they show that when you handwrite a model, your mental model of what the box is doing is actually wrong, and what the real implementations do differs from this handcrafted model in very subtle ways. And these differences will result in wrong outcomes for network verification. So basically, this is a strong argument for the paper. All right, so the last paper in this session is actually slightly different in that it doesn't check network correctness per se. It's more related to do with performance. And this is a paper looking at the correctness of congestion control algorithms, of the implementations of congestion control algorithms. Currently, we test congestion control algorithms by writing fluid flow models for them, writing differential equations and figuring out whether they converge. And then for the implementations, we write unit tests, or we do lab tests with them, or we do wide area tests with them. But there's no real established rigorous testing procedure that we apply. And this paper tries to provide one. And basically, it tries to automatically explore the state space for the implementation of a congestion control algorithm, well, as exhaustively as it can. It tries to cover all possible states. And basically, this is what it tries to do. So the state space for a congestion control algorithm, they call it S, is basically the variables that the congestion control algorithm maintains. Congestion window, slow start threshold, round trip time, and so forth. The state the algorithm is in, and some other variables that each algorithm might maintain. And the goal is to explore all possible combinations of these and check that some properties hold. But of course, the values of these, you cannot just manually set these values. They are driven by inputs from the network. So basically what you have to do to explore these states is to come up with different network parameters. And this is the network parameter space. And basically what they do is they actually just sample all possible network parameters, all possible RTTs, all possible bandwidths, and so forth, all possible loss rates, and they try to increase the coverage of the state space. Okay, and they check for very simple properties. So one property they check is that the congestion window is no larger than 10 to the 7th, right? Or in a congestion avoidance state, you shouldn't be more aggressive than in slow start state. Or whenever you have a loss, you have to decrease your window, not increase it, stuff like this. So very simple stuff. And the algorithm they propose is called ACT. And basically, it's random testing, meaning that you start with a random set of parameters for the network, but then they try to smartly choose the parameters to increase the coverage, right? So first they sample some network parameters. Then they run the actual implementation. So this is implemented in NS3, and it's actually running the Linux kernel implementation of the congestion control algorithm. So this is actually running real code. So they simulate all of this stuff using the actual implementation. And then they figure out which parts of the state space they've covered, right? And then they try to increase coverage using two techniques. They do this parameter estimation thing where they either interpolate or extrapolate, trying to cover new parts of the parameter space. And then they do basically what concatenation means is trying to do two different network parameters back to back, right? So you want to have, I don't know, the bandwidth is now 10 megabits and it drops to 1 megabit to make sure, to try to get the congestion parameters into a bad state and see if you find any bugs. So the real, I guess the real contribution of this paper is these two, A and B techniques to increase coverage, and I'll encourage you, of course, to look at the talk and the paper, and that's really neat. So please have a look in detail. I'll just quickly show you the results, and I'm done. Basically, they show that they cover much better the state space for congestion control algorithms than symbolic execution. So symbolic execution in particular does really, really badly in this example because congestion control works on a lot of data, and symbolic execution chokes when you have many paths. And pure random testing without any feedback, it also does badly. And they found quite a number of cool bugs for these three properties they checked. So for instance, in one case, they found that the C-wind is set to a value that's greater than 10 to the 7th whenever SAC is not enabled. And so in all of these cases, they found also new bugs that people didn't know about, but also existing bugs that were recently fixed. So yeah, that's pretty much it. If you have any questions. Yeah.
Yeah, Nadir from UBC again. I like the NetDiff work, the first one you presented. So they, on the tenant specification, do you support the security extensions? Like the one OpenStack has, security groups?
Yeah, of course, yeah.
Okay.
Yeah,
thanks.
Sure. Thank you. Let me give you
that. Okay, so next up we have Amy from MIT who's going to be talking about the operating system session.
Hi, I'm Amy, and I'm going to be talking about the operating system session. And in particular, all of the papers in this session focus on operating systems in the context of the data center. So let's start by looking at how a data center responds to a request today. When a user clicks on a link in a browser, this triggers a request, which is sent to a front-end server in a data center. The first server in the data center will then contact several other servers within the data center, which can then contact even more servers. And this can involve hundreds or thousands of servers in order to respond to a single user request. Each of these servers runs an application, for example, a key value store, such as memcached, or a database, such as RocksDB or Postgres. Applications have really variable service time. So for example, it might take about 1 microsecond for memcached to respond to a request, whereas for a database query, it might take 5 microseconds or up to some number of milliseconds. Once each server has constructed a response, it will send that back to the server that contacted it, and these will all eventually get sent back to the front-end server. And hopefully this whole process will complete within a fixed latency budget, so for example, within 150 milliseconds. So then we can send a response back to the user quickly. So let's zoom in and look at one of these data center servers. The server is connected to the network via a link. When a packet arrives over the link, it first has to be steered to a specific core, which will handle the packet. The core will then traverse the network stack and arrive at the application that will handle it. Depending on your deployment model, your applications may be running inside containers or VMs. Both virtual machines and containers provide isolation between different applications that are running on the same server. So for example, this would prevent one application from viewing the network traffic of another application. And this is particularly useful in public cloud environments where you might have multiple applications running on the same server that are owned by different organizations. So a container is similar to a virtual machine, but is generally lighter weight. The 3 talks in this session focus on different parts of the operating system. But before we dive into the details of each paper, let's look at the goals that we want operating systems to provide for our applications. Our first goal is that operating systems should provide low latency. And it's important that they provide low latency not just on average or at the median, but that at the tail of the distribution, because responding to one user request can involve contacting so many servers within the data center. So for example, we typically look at latency at the 99th percentile or 99.9th percentile of the distribution. If we look at the overall time it takes to respond to a user request, or a single request in a data center, the network round trip time might only be a couple of microseconds. And the service time for the application could also be only about a microsecond or 2. So it's really important that when the operating system conveys a packet from the network to the application, and in the reverse direction from the application back to the network, that we can complete this with really low overhead. If the operating system adds even a microsecond or 2 of overhead, this can quickly be a significant fraction of the overall response time. The second goal that we would like for operating systems to provide is high network throughput. Links within data centers today can provide throughputs of 40 to 100 gigabits per second, and faster links are on their way. So it's really important that applications can take advantage of this full bandwidth. For example, this could be in the form of sending a couple of large data transfers quickly, or applications might want to sustain really high request rates with lots of small requests. If the operating system takes too long to handle each packet, it can significantly limit the amount of throughput that an application can actually take advantage of. The third goal that we focus on is achieving high CPU efficiency. So instead of leaving some CPU cores idle, we would like to fill all of our CPU cores with different applications. This keeps them busy performing useful application-level work. In addition, we want to make sure that we don't waste CPU cycles performing unnecessary work, such as busy spinning or traversing overly complicated network stacks. And there are 2 reasons why this is becoming more important today than ever before. The first is that rising network speeds mean that applications are increasingly bottlenecked by the CPU rather than the network. The second is that as Moore's law slows, we're no longer getting additional compute resources essentially for free every 18 months. So it's important that we're able to take advantage of the CPU resources that we do have. So why is achieving these goals difficult today? The main reason is the operating system. Unfortunately, there are many opportunities for the operating system to add overheads to the handling of network requests. For example, when requests arrive on the network, you have to decide in what order to handle them. If you do a poor job of scheduling them, packets can queue for a long time, delaying requests. Second, the operating system must decide how many cores to allocate to each application. If you do a poor job of allocating cores across applications, again, requests can queue, and CPU cores can sit idle. And finally, though containers can add isolation to different applications, traversing them can impose overheads on packet handling. The papers in this session focus on each of these challenges. Shinjuku focuses on the challenging of scheduling requests. Shenango focuses on the challenge of allocating cores across applications. And SLIM focuses on the challenge of reducing container overheads. So let's talk about each of these in some more detail. Shinjuku focuses on the problem of scheduling requests. In particular, Shinjuku looks at how you can schedule requests for workloads that have high dispersion or a heavy tail. And what I mean by high dispersion or a heavy tail is generally request distributions that have high variation in the duration of requests. So some requests might be quite short and be able to be handled quite quickly, whereas other requests might be quite long. And our goal with this system is to enable high network performance, so low tail latency and high throughput. So let's look at an example. Suppose that all of your cores are busy handling long requests, and now a short request arrives over the network. In order for this request to be handled, it has to wait for one of the long requests to complete so that a CPU is free to handle it. This is called head-of-line blocking. Theoretical results have shown that the best way to handle this problem is to use preemption. So what this means is that we can temporarily preempt one of the long requests, handle the short request, and once that's done, resume the long request. And this is great because it significantly improves the latency for the short request without significantly impacting the latency for the long request. However, in order for this to be useful in today's environments, you need to be able to have preemption that operates at microsecond granularity to handle requests that take only a few microseconds. And this is actually really challenging and is not possible with existing operating systems. So this is the problem that Shinjuku focuses on, achieving fast preemption on the order of a few microseconds. Shenango focuses on achieving good network performance and high CPU efficiency when running multiple applications on one machine. So for example, suppose you have a machine that's running 2 Memcached applications, each on 2 cores, and 1 database on 1 core. As load varies over time, you might end up in a situation where you have many requests queued for your first Memcached applications, but the cores for other applications are sitting completely idle. In this case, you've done a poor job of allocating your cores across applications. You're wasting CPU efficiency, and you're adding latency for these Memcached requests. So what we really would like to be able to do is to reallocate cores across applications quickly. But again, because requests are only a couple of microseconds long in this environment, we need to be able to reallocate cores equally quickly. So the challenge that Shenango focuses on is enabling these fast core reallocations, which isn't possible with today's operating systems. And finally, Slim focuses on achieving good network performance for applications that are running inside containers. With traditional approaches to containers today, packets must traverse 2 network stacks. First, they must traverse a network stack within the host operating system, and then they must traverse a network stack also inside the container. And the reason for this is that the container must have its own network stack in order to provide the abstraction that applications are running on their own server. And the host operating system must also have its own network stack in order to provide isolation across applications and to enforce routing policies. But unfortunately, traversing both of these network stacks imposes a lot of overhead on every packet. So the problem that Slim focuses on is trying to reduce the number of times that packets have to cross the network stack, while also still providing these isolation and routing properties of existing systems today. So to summarize, we focused on 3 main operating system goals in this session: achieving low tail latency, high network throughput, and high CPU efficiency. And the 3 talks focus on different aspects of the operating system. Shinjuku enables fast preemption, Shenango enables fast reallocations of cores across applications, and Slim enables fast traversal of containers. Thanks. Yeah. So I believe what they do is they don't favor any type of request over another. They just have preemption. Like every 5 microseconds, they will preempt whatever is running if it's still running. But so I think they will still rotate through all of the different requests eventually. But you should see the session for details.
OK. So next up, we have network characterization. Again, this is a bit off the actual conference schedule. So the talk's going to be given by Dave Schaffness.
All right. So yes, I'm Dave Schaffness. I'm going to be talking about network characterization. When I was asked to do this preview, I thought characterization, that sounds like measurements. I do a lot of internet measurement, which is great. And I looked at the session, and then I saw it's really data center measurements with a little bit of internet measurements. So I'm going to kind of change the order according to where my expertise is. So I'm going to start with the internet measurement aspect. So sort of the key things, sort of key challenges here is, for those of you who are unfamiliar, the internet is basically held together by duct tape and glue, enforced by business relationships that are often hidden to us. Bottom line is, as a result, we don't even really know what the internet looks like. We try really hard to measure it. And then we have all of these awful problems like route hijacking that causes all kinds of damage. So basically, we need to be able to model the internet much better to be able to solve these problems. And there's a paper in the session that talks about that. The rest of the papers talk about measurement in a large data center network. I don't think I need to do much introduction given the other sessions on data center networking that have been described so nice and clearly. The challenges here are so many links, conditions extremely dynamic, so things are changing very rapidly, and you need your data, you need your analysis right now, and right now means microseconds. And that puts huge constraints on what you can do. Okay. So I'll start with the stable and practical AS relationship inference with ProbLink. And here the main question is, can we accurately infer AS relationships? And so, sort of the context here is that previous work uses some heuristics, assumptions, and praise. And generally speaking, the overall error rate is not high, is what I meant to say there. The errors that exist are important. And so I mentioned some examples already, like not being able to properly detect route leaks or hijacks, or having poor path predictions. So how many of you have studied BGP? Good number of you, great. How many of you have not? Don't be ashamed. Just a couple people, I am impressed. All right, so you all already, almost all know that this is basically what drives internet connectivity, and it's this crazy protocol that we use in networking that is not actually based on optimizing for anything reasonable in terms of like what we can do via computing, which is like trying to optimize for performance. Instead, it's trying to optimize for policy. And basically, there's a whole lot of issues with it that have been described over many years of papers. But generally, the most important thing you need to know is it's based on economics. And basically, decisions are made based on cost, that companies are trying to make money or reduce the amount of money that they spend. OK, so when it comes to AS relationships, we need to talk about these BGP relationships. So for those who are not familiar, one of the most basic relationships is provider and customer. And the basic idea here is, say if you're Northeastern University, you cannot reach the rest of the internet by yourself. So Northeastern pays a provider to provide that global connectivity. So that's pretty straightforward. And now the customer, say Northeastern, can now access the rest of the internet. There can, of course, be lots of customer and provider relationships. And in certain cases, there's incentive for networks to peer with each other. In the peering relationship, you have networks that generally do not pay each other. So they're willing to exchange traffic with each other, but they will not charge for it. So given this model, you could have a path like this that makes sense. And what about this path over here? Does this path make sense? Yes? No? Oh, you learned about BGP, but you don't remember that, in fact, it makes no economic sense for a peer to forward traffic for another peer. So essentially, this middle peer is doing work for no money, because all of this is settlement free. So basically, when you think about AS relationships, like why do we care about these things, it helps us understand what kind of network paths actually make sense. And when we see things that don't make sense, then that usually tells us either there's a problem in our model or something weird is going on, like, for example, a route leak or a hijack. This is one important thing to remember. So in this case, how does a customer in the bottom left talk to the customer in the bottom right? Well, you can go further up the hierarchy. And now you can follow a relationship that makes sense from a business perspective. So how does all this work to give us global internet connectivity? We assume that there's a tier 1 peering mesh, that essentially there's this set of networks that all are willing to carry traffic for each other and provide global connectivity. And currently there's about 7 recognized ones. There used to be a lot more, but consolidation. All right, so going back to the paper, we want to model AS relationships. We have customer, provider, peer, and we have some other ones we're not going to talk about, sibling and IXP, because they're not really the focus of the paper. But the general way that we model the internet in terms of relationships is something called the Gao-Rexford model. And the idea here is that an AS, or which is to say another word for an ISP, prefers to use a customer path. So they prefer to make money from a customer. Next, they try to peer. So they try to find something that will cost them no money. And then at the end, we'll try to use a provider path, something that costs them money. Generally speaking, this is what is called valley-free routing. The reason is because we tend to draw traffic going from a customer to provider as going up, and traffic going between peers as being horizontal. So this is perfectly fine. There's no valley in this picture. This is also fine, going between 2 peers and then down from a provider to a customer, also completely fine under the Gao-Rexford model. However, doing something like going from a provider to a customer and then across to a peer is not allowed. And why? Where do you see the valley? Well, you can, going up, there's still, it makes no financial sense for this to happen. So when you think about what the paper is trying to do, it's trying to generally be able, or the problem of AS relationship inference in general is trying to find relationships that make sense. Okay, so can we do this? Of course, I'm going to tell you the answer from any one of these papers. Can we do this? The answer is yes, otherwise it wouldn't be here. So how do you do it? One of the key things that they do in this paper is use machine learning. So a lot of the prior work sort of has very fixed notions of how to label different relationships. And this could lead to all kinds of inconsistencies and also has a certain amount of inflexibility. The authors use naive Bayes to probabilistically classify these relationships. And then they throw expectation maximization to learn parameters that form nice clusters that allow you to do these inferences. Whoops. In other details, they talk about why other techniques don't work well and how to use this to do useful things, like I mentioned earlier, classify prefix hijacks and stuff like that. So I'll leave all the details to the actual paper, to the presenters to tell you more about that. Okay, so the rest of the paper is about data centers. One is a really cool question. Is advanced knowledge of flow sizes a plausible assumption? Believe it or not, the answer is yes. This is great news. How do they do it? Can you guess? Anyone? Machine learning. Right. So basically, this is actually, when I read the paper, I thought this is one of the best treatments of machine learning from a networking paper. Usually we just use it as a black box in networking and don't think too hard about it. But this paper goes into a lot of detail with sort of a heavy dose of self-skepticism about why and when it's actually possible to predict flow sizes in advance, and then how you can use that in data center networks to make them more efficient. And then, so there's tons of other details in the work that I won't go into here because this is a preview session. I'm trying to stay on time, and it's late. And they talk a lot about other factors like basically, their approach is workload dependent, and of course, it doesn't work for everything, but there's a large class of jobs for which it seems very useful. All right, so another paper in the session. A simple and scalable method for sensing, inference, and measurement in data center networks. Pretty much what I feel this boils down to is, can we measure everything in real time in a data center network? As I mentioned earlier, super hard because there's lots of things to measure and you need to do it real fast. The answer, again, not surprisingly, yes. How do we do it? Can you guess? Machine learning, yes. So there's a whole bunch of things that are actually coming into play here, some of which are machine learning. There's tomography, which is essentially solving a system of equations where you measure certain paths and between the link segments that overlap. you can essentially solve and assign properties to each link segment through that system of equations. There's probes that allow you to do that. There's lasso regression to reconstruct state from the network based on those measurements. There's an interesting observation about how the topology of fat trees actually makes this a tractable problem. And then we throw some neural networks at the problem, because why not? Apparently, it makes it super fast. And that's really important because it's data center networks and things happen very fast. OK. So last paper I'll talk about, NetBouncer, active device and link failure localization in data center networks. And so here the problem is something failed in your network. Can you identify exactly what is the problem? Obviously, you want to do that quickly so you can fix it automatically, or at least fix it quickly. So again, can we do this? Yes. How do we do it? Oh, it's not machine learning yet. OK, so there's some techniques that are, they basically talk about bouncing packets using a technique called IP in IP, which is exactly what it sounds like, but there's basically hardware support for bouncing packets into certain places in the network to do probes. And once you realize that you can do this, then you have to be very careful about how you plan your probes on that topology to always identify where the link failure is. And the authors note that this would be great if all of the data that you get out of your measurements are consistent. But if, for example, you're measuring loss, there's lots of reasons that loss can happen that have nothing to do with a link failure. And so your data is noisy and you need something else. Guess what it is? It's machine learning. Essentially, the approach here is to solve some of this to address some of this noise using a specific kind of gradient descent that's much more efficient, called coordinate descent. And again, because you need to do this to make things fast. The summary for this session is when you are faced with a hard problem, machine learning. I'll take any questions you have to the extent that I can answer them. Yeah?
How specific are all of these two data center networks as opposed to, say, provider?
I would say almost all of them are data center network specific because they're making assumptions about the topology that just don't exist in, say, the wide area, like fat trees, closed topology, that kind of thing.
OK, we're nearly in the home stretch. We only have 4 more talks to go. So next up, we have Anurag, who's going to be sorry, I again forgot the name of the session. Talking about monitoring and diagnosis.
OK, hello, everyone. I'm going to give you a quick overview of the monitoring and diagnosis session. OK, let's start. You might find it hard to believe, but distributed systems can be just like us, especially when it comes to getting sick. To see my point, just consider the example of a query serving system, a distributed query serving system. If you're a system operator, you might find that the 90th percentile latency has been consistently higher than, say, 10 milliseconds. This is no different from you suddenly waking up with a very bad case of a stomachache. And just like the stomachache, the high latency is symptomatic of some deep underlying cause. Now, in order to determine the root cause behind this particular issue, a system operator might collect different performance metrics like CPU utilization, network utilization, and cache hit and miss counters, et cetera. And this is no different from a doctor checking your temperature and taking note of all your test results, et cetera, to try and figure out what's going on. The main goal, of course, here is to try and figure out what the problem actually was to try and prevent that from occurring in the future. So for instance, over here, the system operator might actually trace the problem to an unusually high number of cache misses, and then try and do some drill down analysis and figure out that the issue is due to misconfigured cache size. This is actually similar to your doctor telling you, looking at your test results, and tell you that essentially you have food poisoning.
And this might help you in preventing future occurrences of this by not eating at shady places. So just like detecting and diagnosing health problems in humans can be pretty challenging, detecting and isolating issues in distributed systems can be pretty challenging too. And the main reason behind this is the increasing complexity of distributed systems. First, these systems operate at massive scales with thousands of applications spanning tens of thousands of servers, communicating at hundreds of gigabits per second. And at such massive scales, even relatively simple problems can be very hard to isolate and find out what actually went wrong. Second, you have very complex interactions between the different system layers now. And this can essentially lead to issues of cascading failures and cascading issues, where an issue at one layer of the system kind of triggers an issue at another layer of the system, and so on until the final problem that actually manifests is very hard to trace back to the original issue itself. And finally, because all these systems have so many different system components, if you try and instrument each of the different system components in order to figure out when a particular issue occurs, this can have unforeseen consequences. For instance, you might end up having unreasonably high performance overheads, or you might end up essentially changing the behavior of the system itself. So to show you how complex these issues can be in the wild, I'm going to go through a couple of examples. The first example is taken from the X-Trace paper from back in 2006, where the problem at hand is essentially a user trying to update a Wikipedia page, but unfortunately, they're not able to view the changes that they've actually made. Now, if you look at a page request on Wikipedia, the request goes through multiple system layers. First, it might go through a cache server, followed by a load balancer, followed by a web server, and finally going to a database server. And each of these system layers have their own caching mechanisms. Now, the reason behind why the user is not seeing their changes reflected could be because any one of these caching layers could be returning a stale result. And actually determining which particular system layer is returning the stale result and isolating the actual server that's the culprit can be a pretty challenging problem. For the next example, take a look at the traffic cascades problem from the switch pointer paper, which essentially shows how complex these issues can be in the networking context. In this particular problem, you have a blue flow contending with the green flow, where the green flow is slightly higher priority and ends up delaying the blue flow, which in turn causes the blue flow to essentially contend with a red flow, which is even lower priority, and therefore the end result is that your red flow is finally delayed. Now, a network operator might look at all of this and try to debug why that red flow is delayed. And to reproduce this issue, he will essentially replay the set of flows that contended with the red flow. Now, the problem here is that in the absence of actually replaying the green flow, the blue flow might actually finish before the red flow even starts, and the network operator might actually observe that the red flow is finishing on time. So actually determining the root cause in the scenario of cascading issues can be a pretty challenging problem, especially when you have a huge network of thousands of concurrent flows. So essentially, monitoring and diagnosis are tools that help in detecting and isolating these issues in large-scale distributed systems. The monitoring is essentially a real-time and online process, which essentially observes the system behavior during its execution, trying to see if there are any anomalies. This is pretty similar to you essentially checking periodically if you have symptoms like rashes. Some examples in the distributed system context, a system like a query serving system might periodically check if the 95th percentile exceeds a certain threshold. A network management system might check if the number of packet drops exceeds a certain threshold. And a task scheduling system might check if a particular task spends too much time in the queue before it gets scheduled. A diagnosis, on the other hand, is an ad hoc and offline process. And this particular process is collecting diagnostic information after the anomaly has already occurred. So essentially, you would only check for your own temperature if you already are feeling feverish. You wouldn't do it before that. So the main goal here is essentially to determine the root cause of the particular issue using some form of drill-down analysis. For instance, the doctor might take a look at your blood test results, your temperature, et cetera, and correlate it with your symptoms, try and figure out what disease you actually have. In the same way, in a distributed system, for instance, in a querying serving system, once you have seen the symptom of unusually high latency, you might actually look at different performance counters, look at the number of cache misses, and you see that you have an unusually high number of cache misses. And then you do some further drill down analysis to figure out that this was due to some misconfigured cache size. OK, with that gross oversimplification of what is actually a pretty challenging field, I'm going to take a quick look through some of the exciting work on monitoring and diagnosis at NSDI this year. So the first talk in this session is going to be about end-to-end I/O monitoring on a leading supercomputer. And this essentially bridges the gap between application-oriented I/O monitoring tools, which essentially do not take into account inter-application interactions. And on the other hand, you have back-end-oriented tools which are essentially ill-equipped to perform analyses at the application layer, such as detecting inefficient I/O requests at the application layer. And their solution, which is called Beacon, is to essentially combine both front-end tracing tools and back-end profiling tools into a single multi-layer system that is capable of doing I/O resource monitoring and diagnosis. Now, Beacon is a system that has been deployed for a period of over 18 months on a 40,000 node supercomputer. And as a consequence, they have a lot of interesting stories to tell. So if you want to learn more about it, please attend the talk. The next talk in this session essentially addresses an important problem in existing tools, which only tend to focus on what they call functional causality, which is essentially asking the question why a particular computation has a certain result. What is essentially missing is the analysis of temporal causality, which aims to look at the timing and the order of events in order to figure out the root cause behind certain problems. The approach that their system Xeno takes is essentially to employ a new technique called temporal provenance, which is able to reason about both functional causality and temporal causality in the same stack. And by doing so, they're able to show that they can diagnose a large class of problems from performance problems from Google Cloud Engine. And if you want to get a good insight into what kind of problems they're able to solve, again, please attend the talk. The next talk in this session will be about Conflow, which will be given by me. And that describes a system which is essentially a distributed monitoring and diagnosis stack for high-speed networks. The problem in designing such a stack for high-speed networks is that essentially on one hand, you have to handle millions of packets per second. You have to essentially look at millions of packets per second if you want to essentially detect problems in them. And on the other extreme, you essentially have to, in real time, analyze, monitor, and debug a large class of distributed monitoring and diagnosis applications using minimal CPU resources. Conflow is able to resolve this particular challenge by exploiting workload characteristics of network telemetry data. For instance, it makes the observation that once this data is processed by the stack, it is no longer updated, and the fact that attributes of interest that need to be analyzed in the network traffic tend to be of fixed size. And by exploiting these properties, it is able to not only capture packets at a line rate for larger than 10 gigabit links on a single CPU core, but it is essentially also able to support a wide range of network monitoring and telemetry applications by exploiting the telemetry data that's embedded within packet headers. The last talk in this session will talk about the deterministic TCP replay for performance diagnosis. Now, TCP is a constantly evolving protocol and is typically error-prone, at least in the data center context. However, deterministically replaying a large network of TCP connections can be pretty challenging because of what the authors refer to as the butterfly effect, where even a small timing variation between the actual runtime and the replay can lead to a completely different state in the replay. And the authors essentially propose a new system called Ditter, which resolves this problem by replaying these connections individually and then capturing all of the interactions between the individual connections and the network and the application separately. And by employing this approach, Ditter is able to diagnose a large class of TCP problems with very minimal CPU and storage overheads. And again, if you want to know more about how Ditter is able to do so, please attend this talk. That's all I have. Thank you so much. And I hope to see you all at this session. Thank you.
Questions while Cheng is setting up? Okay, so next we have Junchen, who's going to be talking about the improving machine learning section. So as opposed to Dave's talk where everything uses machine learning, this one's more about how you get machine learning to work.
Okay, good. Well, I figured out this is already like twice the length of a normal session, so I absolutely admire that. Okay, so I'm going to talk about topics around building systems for machine learning. Again, we're now building systems not for someone else. We're building systems for ourselves because we're using machine learning everywhere. All right, so as many of you may realize, machine learning systems is one of the hottest topics in systems communities in general. Now, this is just in the last 5 years, almost every top system conference has at least one session specifically on systems for machine learning. This is not general cloud systems applications. This is systems for machine learning, like deep learning or graph mining. So if you're interested in machine learning and systems, this is really a good time. Now, this session on Wednesday includes 3 papers, and I will briefly explain these papers in the next few slides. But before we dive into details, let me first talk about some of the general common themes behind these papers. Now, what is an ML system? An ML system is basically a software system sitting between ML applications and ML users and the underlying hardware. Okay. The goal here is to maximally optimize the ML application performance, typically like how long you train a model, by fully utilizing the underlying available resource, and while providing a user-friendly programming interface. So good ML systems obviously would be a function of the ML application needs and the user demand and the underlying available hardware. So naturally, many of the innovations around ML systems have been basically spurred by the changes in the ML tasks or user needs or underlying hardware. Now, this is also certainly the case of the 3 papers in this session. Now, one of the changes that ML tasks that has direct linked to the 2 of the papers, the lead 2 of the papers in this session, is the rise of deep learning. Okay? Especially training deep neural networks, or DNNs. Now, let me briefly explain how to train a DNN with this graph. This is image classification, a typical use case of DNN. The training process basically alternates between 2 processes, a forward process and a backward process. Okay? And it keeps iterating until the model converges. Now, in the forward process, a DNN basically takes as input a bunch of images, each represented by a pixel matrix. Okay? And a DNN is basically a sequence of nonlinear transformations, applying nonlinear transformations on the output, on the result of the last layer. So basically, at the end of the day, each input matrix will get a lot of nonlinear transformations layer by layer and eventually get a prediction. Now, once you get a prediction, you can now compare that prediction against the ground truth labels and now get the error or the difference. And that difference, that error, will be propagated backwards through these layers to update the parameters in the hope that the next time you do the forward propagation, the result will be more accurate. Okay? So at the end of the day, what that means is over the training process, the training accuracy will become better and better with more and more iterations. So let's talk about the first paper now. The first paper presents a system called Janus. The paper is motivated by basically 2 competing trends in deep learning frameworks. On one hand, there are a lot of deep learning frameworks like TensorFlow, MXNet, basically formulate a deep learning process as a static configuration graph, okay? Which is very amenable to kind of a graph, symbolic graph optimization, and has very high runtime performance. But on the other hand, however, expressing everything in static computation graphs, which will be substituted with real data only in runtime, makes debugging very difficult. Makes the user makes it very difficult for user to do debugging in real time. because users are not actually running numeric computation while formulating, so defining these neural nets. So many users actually stick to imperative APIs like PyTorch or NumPy because they give users more flexibility. Now, in short, basically, there's a gap between performance optimization, which requires writing programs in symbolic graphs, and user friendliness, which requires writing programs with imperative APIs. Okay. Now, this paper, Janu's first paper, is an attempt at bridging this gap. The key idea here is to still keep the imperative API while converting every imperative program into a static data flow behind the scene. Okay? So basically, user can still write programs with imperative interface while enjoying the same performance as state-of-the-art deep learning framework. Now, the second paper, called Tiresias, is a GPU cluster manager to minimize the deep learning training time when you have multiple deep learning jobs running on the same GPU cluster. Now, resource management is a very classic problem, right? So why do we need a new resource manager for deep learning and GPU cluster? Well, the conventional wisdom for job scheduling is that you basically assume you have some sense of the resource demand of a job, of a training job, right? But the problem of deep learning is training a deep learning model will never converge as smoothly or monotonically as training a traditional model, traditional ML model. So it's very hard to predict the time. Moreover, loading a DNN onto GPU actually is much more costly and slower than loading any other program onto CPU in a data center. So basically, that means preempting jobs frequently is no longer possible. Okay? So this is, again, it is an example where you have changes on the application layer, the ML tasks, and changes in the hardware, available hardware, and that creates some new challenges for the ML system. And in this case, what the paper shows is that it is possible to kind of adapt the traditional scheduling algorithms to this new environment and achieve much shorter training time for deep learning models than any other traditional baseline algorithms. Now, the final paper presents a system called Blast on Flash. This is a system library built specifically for like ML tasks that are memory bound rather than CPU bound. Okay, so if a task is memory bound, what I also found out is that users often are forced to rewrite their programs to run the program on a cluster rather than as a workstation because, well, the workstation doesn't have enough memory for that. So the goal here, obviously, is to allow users, very ideal goal is to allow users to write these memory-bound programs and run them on single workstation by using the seemingly like slower SSD storage. This is made possible by the exponential growth, the recent exponential growth of the PCIe bandwidth that's connecting these SSD storage. So that large matrices can be stored across multiple SSDs while being accessed with high throughput as if these matrices are stored in memory. Okay? And this paper also leverages the fact that a lot of ML tasks use this library called BLAST, which is a set of operations on top of matrices and vectors. And they use BLAST very intensively. So what that means is it allows the authors to simply optimize the BLAST performance, the BLAST libraries, on top of on large SSD resident matrices. So in short, these papers are basically very excellent examples of this rich and exciting research area. And looking forward, there will be more and more works that are driven by the kind of increasing diversity of ML tasks and more heterogeneous operational environments. And of course, the benefit can flow the other way around. Like David said, one can build better systems by using ML. And again, this is not too late to jump into this area. See you on Wednesday afternoon. Thank you. Any questions?
OK, 2 more talks. Hang in there, please. So next up, we've Radhika, who's going to be talking about network functions.
Hi, everyone. Thanks for still staying here beyond 9:30 p.m. So yeah, I'm going to give you a preview on the network function session. So how many of you have heard the term network functions and have wondered what they are and how they're different from middle boxes and why is there such a big hype around them? So I used to wonder all of this before I prepared for this preview session. So let me start with some background on explaining what I've understood about network functions. Okay. Oh, I didn't plug in my clicker. Okay, I'm too sleepy as well. Okay, so this is the conventional view of networks that we're used to seeing in a textbook, which basically comprises of switches and routers as the only entity inside the network that provide connectivity between the endpoints, that is our computers or data center servers. And the main functionality that such a simplistic network provides is data delivery between 2 endpoints. But such an idealistic view of a network ignores various other functionality that we need from today's network. And therefore, a more realistic view of a network looks something like this, where in addition to having switches and routers that are now represented by these black dots, we have other entities inside the network called middle boxes, represented by these colorful rectangles, that provide functionality other than just data delivery. So for example, we can have middle boxes like IDS and firewall that can be used to enhance security by identifying and blocking unwanted traffic. We can use middle boxes to improve performance. For example, caches can be used to load content faster, and WAN optimizer can be used to reduce bandwidth usage. Middle boxes can also be used to provide application support for legacy applications that do not implement some required protocol. For example, we can use an SSL proxy for HTTPS support. And there are multiple such examples of middle boxes. So middle boxes have emerged as the predominant way for deploying new network functionality in the networks. And a survey conducted for SICOM 2012 showed that 1/3 of all network devices in an enterprise are middle boxes. So they're exceedingly common. Now, the way that we have been implementing middle boxes has evolved over the years. So middle boxes were traditionally implemented as dedicated hardware boxes. And the use of hardware was to keep up with the high rate at which packets arrive and the high rate at which they need to be processed. But while hardware provided us good performance, the inflexibility of hardware made it extremely difficult to update the middle boxes and to deploy new ones. Therefore, driven by the need for flexibility, and with Moore's law that was still alive at the time, speeding up software, we moved away from using dedicated hardware for middle box implementation towards using software. And this move from hardware to software resulted in rebranding of middle boxes as network functions. So coming back to our picture of the network, instead of having these individual hardware middle boxes deployed inside the network, we move towards software network functions, which are essentially middle boxes implemented in software and often deployed as virtual machines inside general purpose servers. And because of the use of virtual machines, this is often termed as network function virtualization. Now, this move from hardware to software resulted in a number of benefits. And one of the main benefits was programmability. It allowed us to easily update and create new NFs doing all sorts of things. It also made it much easier to deploy, configure, and manage network functions. So for example, If I want all of my traffic to first go through a firewall and then a cache, I can simply do so by updating my software and creating what we call a service chain. And if the rate of the incoming traffic increases, I can scale up and keep up with that by simply spinning up more NF instances. So these benefits have resulted in network functions being widely adopted in both carrier networks, for example, AT&T, and by cloud providers, for example, in Microsoft Azure. However, this move from hardware to software has come, along with its benefits, has come with some cost. Because sort of implementing complex network functions has now become so much easier, and we can chain them in convoluted ways, and we can spin up multiple instances, all of this has made state management somewhat complex and costly. Second, as is expected from a move from hardware to software, the performance has now become more variable or unpredictable, which makes it hard to estimate how we can provision resources. And finally, the move to software has had some impact on performance, especially now when traffic demands are constantly increasing, but Moore's law is dying, which means that we can't just throw more general purpose compute resources in order to keep up with the high demands. And because of the importance of network functions, the benefits and opportunities that the use of software provides, and these open-ended challenges, network functions has become a very rich area of research for the networking community. And over the last 5 or so years, we have seen multiple papers that have tried to address these challenges in some way or another. So for example, we have had papers that build new frameworks to do state management when we are scaling up network functions or when we are doing failure recovery. We have had papers that try to understand NF performance either by analyzing the worst case algorithmic complexity or by measuring runtime performance. We also had papers that try to provide formal guarantees about the correctness of NF implementation or configuration. And we've had papers that propose new ways of implementing NFs for getting high performance. And this list of papers and categories is certainly not exhaustive. In this year's NSDI, we have 3 papers on network functions that significantly advance the state of the art in dealing with each of these challenges. So let's take a quick look at them one by one. So the first paper is titled Correctness and Performance for Stateful Chained Network Functions, and it deals with the first challenge of complex and costly state management. More precisely, it asks, how do we manage state that is shared across flows and across NF instances without incurring high overhead? So what makes this work different from prior work is that it considers the fact that the state that an NF manipulates can be shared across flows and therefore across multiple instances of an NF. This is something that prior work has largely ignored, which makes this work rather important. The second paper in the NF session is titled Performance Contracts for Software Network Functions, and it aims to accurately predict NF performance without running the NF itself. It draws upon prior work that try to understand the worst case network function performance and that try to verify the correctness of NF implementation. So it draws upon these works and it builds a framework that can precisely characterize NF performance for arbitrary workloads. So this is something that no prior work has done, making it extremely useful. The final paper in the session is FlowBlaze that aims to navigate the fundamental trade-off between the flexibility of software and the performance of hardware. So it basically leverages certain properties of network functions to abstract higher level abstractions, expressive abstractions that makes it easier to write code on programmable hardware, which in general is difficult. So to recap what we learned in this preview talk, so middle boxes are entities that are commonly deployed inside the network to achieve all sorts of functionality other than just data delivery, and they're exceedingly common. And network functions are essentially middle boxes implemented in software. And the use of software provides important benefits such as programmability and ease of management. Because of these benefits, network functions are being widely adopted in both carrier networks and by cloud providers. But the use of software also brings with it multiple challenges that have largely been unresolved, making this an important area of research. And in this paper, in this NSDI, we have 3 papers that significantly advance the state of the art in dealing with these challenges. Please attend the NF session at 5:10 p.m. on Wednesday to learn more about these works. Thank you.
Okay, so if you have questions, you should ask. And next we have what is the last but somewhat exciting talk of this previous session on wireless applications. So this is a bit different from what Dinesh talked about, where he was talking about wireless technologies. This is about how you can use wireless to achieve various things. And so giving the talk, we have Shadi.
About wireless applications. And when I signed up to do this preview session, I didn't really think about how to provide background on wireless applications in 10 minutes. So we're going to do our best. And kind of like what Dinesh did, I'm going to provide some really high-level basic intro to some of the concepts you need to understand these papers in the session. And then we'll go through each of the papers and kind of the problems they're focusing on specifically. So it's going to be super high level. Hopefully will help you understand the session. So if you have to find one unifying thread from this session, it's broadly that radio waves exist and you can send information over them. But when you take these two things together, there's actually a lot of really cool applications that you can build using wireless technologies. So we can do things like locate objects in the distance and detect their properties. It's kind of what we do with radar. We can read identification from RFID tags. And of course, wireless communication is ubiquitous in modern society. And so let's talk about how we go about building wireless systems in practice. Unfortunately, it's not as easy as having a transmitter and receiver and signals go in a straight line. Radio waves are waves, and so they bounce off things. So you have multipath effects, where when you send the signal out, you'll have a direct path that your signal will propagate towards your receiver, but it might also bounce off walls, ceilings, and so forth. This can be either good or bad, depending on what you're trying to do. Similarly, we have backscatter. And so when your signal hits an object, it's going to reflect back as well. This is one of the things that allows us to do localization using radio. So an example of this that we've already seen today is how RFID tags work. So RFIDs, very simple, cheap devices. You hit them with some radio RF energy. The RFID tag harvests that energy to power up and modulates the response back. And this is how we get information off of an RFID tag. Another principle that we need to keep in mind is attenuation. When you send a signal, as it travels, the energy dissipates. So just like it's harder to hear sounds that originate from far away, we have the same thing that happens with RF. And at higher frequencies, this is more pronounced. The higher the frequency to first order, the more loss you have along the path. Now, things we can do to get around this, we use antennas. And antennas basically focus energy. So the antenna that you have on your cell phone is probably a low-gain, omnidirectional antenna, which makes a lot of sense for mobile applications. But if you're dealing with really high frequencies and need to be able to project your signal in a given direction, you might use a directional antenna that focuses the energy and allows you to kind of overcome that attenuation loss. So one of the things that we benefit from from directional antennas is spatial reuse. So an example we'll see in a little bit is if we had a very narrow beam that we're transmitting our signal over, we're able to put multiple pairs of transmitters and receivers on the same frequency within close proximity to each other, and we can effectively double the throughput of our system just because we have multiple paths available to us. And there's many different ways and tricks that you can get multiple channels in radio. And so this same principle also applies to cellular networks. The reason that they're called cellular networks is because we have cells that are defined where each one is using a specific frequency, and we arrange the cells such that no two neighboring cells or nor two adjacent cells are using the same frequency, and that avoids interference at cell edges. And so let's talk about the first set of problems that two of the papers in this session address. So finding things with radio waves. The basic idea here is we're going to bounce a radio wave off of a thing. We're going to estimate its location based on some of the reflected energy from this. And so this is different than what we do with GPS, right? So we're not trying to find ourselves, we're trying to find objects within our environment. And there's lots of tricks that you can do this. You can send it a pulse, and you can measure how much time it takes to come back to you. This is called time of flight. You can measure the angle of arrival for the reflected energy, phase shifts, things like that. But in all cases, what we'd like to have is high resolution, high accuracy, low latency, and low power consumption. And so there's lots of different ways at which we can build systems to achieve these goals depending on the needs of our application. We could use an ultra-wideband radio, which the way that works is imagine we're sending out a short pulse over a very wide bandwidth at low power. And this allows us to get really high resolution ranging at low power, but it only works over relatively short ranges. RFIDs are another piece of the puzzle that we could use for this. They're super cheap, and they have this nice benefit that we might be able to get a target's identity along with its location if we're using it in some kind of localization system. So the first two papers in this session really look at, given all the pieces, how can we put together systems that work within specific application domains to provide localization. And so the first paper, TrackIO, Tracking First Responders Inside Out, is a system that's trying to look at the problem of how do you identify the locations of emergency workers inside a building that's in an unknown environment without any infrastructure. And so the key idea behind this paper, and what makes it really cool, is they're imagining a scenario where all you have to do is show up with a UAV that has an ultra-wideband ranging beacon on it. Your emergency workers on their helmets might have some kind of ultra-wideband beacon as well. And then they use the motion of the UAV to determine the locations of the emergency workers closest to the edge of the building, which are still in range of that first hop. And then once you know the locations of those workers, you can estimate the locations of workers further inward recursively. And so this is a really interesting application of RF localization. Looking kind of at another example of this, what if we want to use RF localization for robotics applications? So here we need extremely precise measurement of the location of objects. And this paper, 3D backscatter localization for fine-grained robotics, they're actually able to demonstrate a system that uses RFID tags to track multiple objects in real time with sub-centimeter resolution. So they can put RFID tags on, for example, 2 micro UAVs flying around and that precisely track their locations. Or if you have a pair of robotic arms that wants to hand off one object to the other, it needs to know the location of that object, and they're able to demonstrate that they can achieve this with their system as well. How exactly do they do that? You should go to their talk and find out. So another application for wireless that we're all familiar with is communication. We want to push as many bits through the air as possible. And so if you look at some widely deployed wireless systems today, like 802.11ac, Wi-Fi, or LTE from release 14, to first order approximation, you might get a gigabit per second out of these radio systems, which is pretty good, but we'd like to do better than that. But all of these radio systems are operating broadly within about 600 megahertz to 6 gigahertz to first order. And there's lots of tricks that we've used over the years to get higher throughput out of these systems. We can use MIMO, we can use higher order modulation, but the easiest thing to do is really just throw more bandwidth at the problem. If we remember the Shannon-Hartley theorem, we get additional channel capacity linearly with relation to how big our bandwidth is. And so if we want to use more bandwidth, though, we need to move up the frequency spectrum because there's just not that much available below 6 gigahertz. And so this is what millimeter wave does. So the millimeter wave radios, we're using bandwidths over gigahertz, and practical systems are able to achieve multiple gigabits per second of throughput, which is really quite cool. But once we do this, we have some new challenges, and we have some new opportunities. Higher frequency means more attenuation, which means we have to use highly directional antennas to direct our, to be able to close our links. But the benefit of this is that we're able to gain even more throughput for our system through, through spatial reuse. But the challenge is we have to make sure our transmitter and receiver are actually aligned so they can close the link and communicate. Otherwise, nothing's going to work. So in many-to-many beam alignment in millimeter wave networks, as the name implies, solves the problem of how you take a system that has multiple millimeter wave access points and multiple millimeter wave clients and simultaneously performs beam alignment across all of them. It takes that a step further, though, and remembers that we're trying to optimize the throughput globally across the entire system. And so what it does is it determines both the available paths, direct paths between every AP and every client, as well as the indirect paths that take advantage of reflections within the environment to figure out what are the set of available paths, and then centrally computes the optimal scheduling of the RF paths to achieve the best throughput for the system. And so finally, once we're able to build wireless links, we want to use them to do things like connect people to the internet. And so there's about 5.5 billion mobile subscribers today. About half, a little less than half the world's population is on the internet, and they're largely getting access through wireless networks, mobile networks in particular. That's pretty impressive for technology that's less than 30 years old. But mobile networks have stopped growing, and the cost of building out mobile infrastructure at the same time is coming down. And what that's allowed us to do is enable new classes of actors to go out and build mobile networks when they couldn't before. 10 years ago, a rural base station would cost $500,000 to build. Today, we can do that for $20,000. And again, this creates new challenges and new opportunities. With these new actors who are able to build cellular networks, we're creating new business models to provide sustainable coverage in rural areas that are previously underserved. But the people who are doing this aren't telcos. They may not have the experience that we typically expect is required to build a cellular network. So we need to simplify their operation of networks and reduce remaining barriers to entry. And so last paper of the session, Scaling Community Networks with Community Cellular Manager, is tackling the problem of how you expand rural service to rural areas. And the idea here is that we are going to build a new network architecture that's well suited for community-based networks, and we're going to enable cooperative interaction between telcos, which hold some scarce resources that are needed to run a cellular network, and community networks. And by doing this, this paper shows that it's able to build a system that supports some of the important use cases for rural areas, and also is able to support the largest community cellular network deployed to date. So wireless applications session, it's at 3:35 on Thursday, the last session. Is it the best session? You have to come there to find out. But it's definitely an interesting set of papers and some really socially important topics, so I hope to see many of you there. Thanks.